A galaxy exists that is so strange and unlikely that it breaks all the rules we thought we knew about how galaxies form. At its centre is a perfect golden core, surrounded by a flawless ring of blue stars with a huge empty space in between. This is Hoag's object, a cosmic mystery located 600 million light-years away. From its impossible symmetry to its unusual mix of stars, nothing about it should exist. Yet, it is there, quietly challenging everything we think we understand about the universe. What makes it so mysterious? Before we begin, tell us in the comments below where in the world you're watching from and what time it is there now. Now settle in for a fascinating journey to uncover the mysteries of the Hoag's object. The first time anyone laid eyes on what we now call Hoag's object was a moment that, in hindsight, seems almost like a quiet ripple that would one day shake the foundations of what astronomers thought they knew about galaxies. It all began in the year 1950, when Arthur Hoag, an American astronomer with a careful eye and a deep curiosity about the universe, was working with the 48-inch Schmidt telescope at the Palomar Observatory in California. At that time, telescopes were the windows through which humans could peer into the vast, seemingly infinite ocean of stars, and each night of observation was an adventure. Hoag was not on a hunt for the unusual. He was not searching for cosmic oddities or galaxies that might defy classification. He was simply studying the stars, looking to understand more about the patterns and structures that make up the tapestry of the night sky. On that particular night, as he carefully exposed photographic plates to capture the faint light of distant celestial bodies, nothing initially appeared out of the ordinary. Among countless other faint points of light, one object at first seemed like just another unremarkable dot, a small smudge of light that might easily have gone unnoticed. But Hoag, trained to notice details, eventually saw something that made him pause. There, on the photographic plate, was a small, bright, round ring encircling a densely packed core. The ring itself glowed with an even, almost perfect brightness, while the core seemed compact, more like a galaxy than a star or gas cloud. In the early moments, Hoag considered the most logical explanation available at the time. Perhaps it was a planetary nebula, a glowing ring of gas and dust expelled by a dying star. Planetary nebulae were known for their round, symmetrical shapes, and this explanation would have fit neatly into existing astronomical knowledge. It was a reasonable assumption because many planetary nebulae present as bright circular formations when observed through telescopes, and they often have a luminous centre surrounded by a glowing envelope. Yet, something about this particular ring did not sit right with him. It was too large, too bright, and the central core did not resemble a single dying star, but rather looked much like a compact galaxy, crowded with stars and concentrated in a way that planetary nebulae almost never were. Arthur Hoag was meticulous by nature, and he did not rush to judgment. In the 1950s, astronomers did not have the luxury of modern instruments like space telescopes, digital sensors, or supercomputers to analyze astronomical data. Everything had to be painstakingly recorded on photographic plates. Measurements of brightness were taken with care, and the slightest anomaly required patience and repeated verification. To declare an object something new or unusual meant enduring hours of careful work, careful cross-checking, and often consulting with colleagues. Hoag noted the object's exact position in the sky, located in the constellation Serpens, and meticulously described its unusual structure. Still, without the tools to fully explore its nature, he could only suggest possibilities. In his scientific paper that year, he referred to the object cautiously, calling it either a ring-shaped galaxy or perhaps a planetary nebula. In doing so, he planted the seed of a mystery that would grow in intrigue for decades to come. As the years passed, the photographic plates containing Hoag's object became a source of fascination for astronomers. At the time, most galaxies astronomers knew about were messy, irregular, or chaotic. Spiral galaxies twisted and curved with arms that often looked uneven, elliptical galaxies spread out in soft, fuzzy shapes, and irregular galaxies appeared almost like scattered clumps of stars and gas. None of these resembled Hoag's object. Its symmetry and perfection were almost artistic, as if it had been drawn with the careful precision of a compass. The ring was nearly flawless, and the bright round core in the centre was sharply defined. For some astronomers, the object seemed too perfect to be real. Perhaps it was an optical illusion, a defect in the photographic plate, or some strange quirk of perspective that made the ring appear complete. Some wondered if the telescope itself had introduced an artifact. Others simply marvelled and filed the images away, unsure of how to classify what they were seeing. It was not until the 1960s and 1970s, when telescopes became more powerful and spectroscopy, the study of the light emitted by objects in space, became more advanced, that astronomers began to realise that Hoag's object was not an optical trick or a faint, unusual nebula. Spectroscopic measurements revealed something astonishing. The light coming from the ring was not from a nearby object, as it would have been if it were a planetary nebula, but from stars situated hundreds of millions of light-years away. By measuring the redshift of the light, the way wavelengths stretch as objects move away from us due to the expansion of the universe, astronomers determined that this ring-shaped galaxy lay roughly 600 million light-years from Earth. The sheer scale was staggering. The ring itself spanned tens of thousands of light-years across, dwarfing the tiny planetary nebulae of our own galaxy, which typically extend only a few light-years. Arthur Hoag could hardly have anticipated the magnitude of what he had discovered. He had stumbled upon this object purely by chance, his gaze drawn by something unusual in the corner of a photographic plate, rather than by an intent to uncover the extraordinary. Yet, sometimes in science, progress comes precisely from such moments. A chance observation, a careful eye, and the curiosity to note what others might overlook. Hoag's attention to detail ensured that the object was recorded and remembered, setting the stage for decades of inquiry and wonder. Even from the earliest images, one feature of Hoag's object was immediately striking. The space between the bright ring and the central core was almost completely empty. Unlike most galaxies, where stars, gas clouds, and other celestial material form a gradual transition from the dense core to the outer arms, here there was a void. A seemingly perfect gap separated the golden, densely packed centre from the brilliant blue ring of younger stars. This stark emptiness only deepened the mystery. Astronomers had never seen anything like it. The clarity of the photographs made the image appear almost unreal. It was as if the universe had drawn a circle and carefully erased the space in between, leaving only the core and the ring. Over the following decades, as larger ground-based telescopes came online, and CCD imaging technology, allowing for higher resolution digital captures, became widespread, Hoag's object stood out more and more clearly as a unique and baffling example of galactic structure. It did not conform to the traditional categories astronomers used to classify galaxies. It was not a spiral galaxy. It had no twisting arms, no central bar, no visible disk extending beyond the core. It was not an elliptical galaxy either. The outer ring was too sharply defined, too bright, and unlike any known elliptical or lenticular system. Even among other ring galaxies, Hoag's object was unlike any known example. Most ring galaxies arise from violent collisions between galaxies, which send waves of stars and gas outward to form a ring. These galaxies usually bear scars from the cosmic encounter, streams of debris, irregular ring shapes, or remnants of the disrupted galaxy. Hoag's object showed none of these signs. Its ring was smooth, pristine, and seemingly untouched by any violent event. It appeared as though it had existed in perfect equilibrium for eons. The universe rarely offers such puzzles. In the early 1980s and 1990s, as technology continued to improve, astronomers revisited Hoag's object with fresh eyes. Larger telescopes and sensitive imaging revealed even more details. The outer ring contained thousands of young hot blue stars, while the central core was densely packed with older yellowish stars. The transition between the two regions was abrupt, with the empty space in between standing out as stark and mysterious. The question of how such a structure could form naturally without evidence of collision, disruption, or other dynamic processes challenged every conventional theory of galaxy formation. The object became a kind of cosmic enigma, a puzzle that resisted all attempts at explanation. Then, in the year 2002, the Hubble Space Telescope turned its extraordinary lenses toward Hoag's object. By this time, the object was already well known among astronomers as a peculiar and puzzling galaxy. Hubble's high-resolution imaging revealed the object in unprecedented detail. The central core appeared oval-shaped, densely packed with golden stars. Surrounding it was the nearly perfect blue ring of young stars, glowing with vibrant intensity. The empty gap between the core and the ring was so pronounced that it almost seemed deliberate, a cosmic boundary separating two entirely different stellar populations. The Hubble image added a new layer to the mystery. In the background, a smaller ring-shaped galaxy could be seen, bearing a striking resemblance to Hoag's object itself. Whether this was a chance alignment or something more profound was unknown, but the visual echo added to the sense of wonder and complexity surrounding the object. Arthur Hoag, by then long retired from active astronomy, had no idea that the discovery he had made decades earlier would become such an enduring enigma. His initial observation, a small bright spot on a photographic plate, had blossomed into one of the most fascinating puzzles in extragalactic astronomy. Though he never fully explored the object himself with the advanced tools that later generations would use, his careful documentation ensured that his name would remain forever associated with the galaxy. Hoag's object became a case study in the importance of curiosity, careful observation, and the willingness to record the unusual, even when its significance is not immediately apparent. The legacy of Hoag's object is not just in its striking appearance, but also in what it represents for our understanding of galaxies. It challenges astronomers to question assumptions, to consider that the universe may be far more varied and imaginative than traditional classifications suggest. The perfection of its ring, the density of its core, the emptiness of the space in between, and the almost eerie calm of its structure all combine to make it a symbol of cosmic mystery. Unlike the chaotic aftermath of collisions or the irregularity of most galactic structures, Hoag's object is a quiet marvel, a cosmic artwork that seems to have formed according to rules that we do not yet fully understand. Through the decades, from the initial photographic plate in 1950 to the Hubble image in 2002, astronomers have studied, measured, and speculated. Yet many questions remain unanswered. How did such a perfectly symmetric ring form? Why does the central core remain isolated from the ring? What processes allowed the galaxy to maintain such a pristine appearance without apparent disruption? Even with all of the advanced tools now available, from space-based observatories to computer simulations, Hoag's object continues to defy simple explanations. Its beauty is not merely aesthetic but intellectual, compelling scientists to consider the extraordinary possibilities of galactic evolution. In many ways, the story of Hoag's object is a story about the nature of scientific discovery itself. Often, progress does not come from what is expected or sought, but from what is noticed by careful eyes that observe without prejudice. Arthur Hoag's discovery was accidental in the sense that he was not looking for the impossible, yet it illustrates the importance of attention to detail, persistence, and curiosity. One small, faint object on a photographic plate led to decades of inquiry, debate, and fascination. It reminds us that the universe is full of surprises, and sometimes the most profound discoveries arise in the quiet corners of research, where patience and diligence allow the unusual to reveal itself. Hoag's object remains a highlight in the field of extragalactic astronomy. It serves as a benchmark for the limitations of our understanding and as a challenge to the theories that explain galaxy formation. While most galaxies fit neatly into categories such as spiral, elliptical, or irregular, this remarkable object refuses to conform. Its almost artistic symmetry, the clear separation between core and ring, and the unexpected echo of a similar galaxy in the background continue to captivate astronomers and enthusiasts alike. Every new observation deepens the mystery, reinforcing the notion that the cosmos can produce structures of exquisite precision and unexpected elegance. The discovery also highlights the evolution of observational astronomy itself. In the 1950s, a single astronomer with a Schmidt telescope and photographic plates could spot something extraordinary, but the tools to fully understand it did not yet exist. By the 1960s and 70s, improvements in spectroscopy and the development of larger telescopes provided new clues about distance, composition, and scale. By the 1980s and 90s, digital imaging allowed for greater clarity and measurement precision. And finally, in the early years of the 21st century, space-based telescopes like Hubble provided stunning images that confirmed and deepened the enigma. Each generation built upon the careful work of the previous, demonstrating how scientific knowledge is cumulative, yet how some discoveries remain tantalizingly elusive, even with the best available technology. The legacy of Hoag's object, then, is twofold. It is a legacy of beauty and mystery, a celestial structure that is as visually stunning as it is intellectually provocative. And it is a legacy of the scientific method, showing how careful observation, patient measurement, and rigorous documentation can transform a faint anomaly into one of the most studied and admired phenomena in the universe. From a faint, curious, bright ring on a photographic plate to a galaxy celebrated for its symmetry and puzzling formation, Hoag's object reminds us that the universe still has secrets to reveal, waiting for those with the eyes to see them and the patience to wonder. In summary, what began as a quiet moment in 1950, with Arthur Hoag peering through the 48-inch Schmidt telescope at Palomar Observatory, eventually became one of the most famous "how is this possible" cases in astronomy. It is a story of chance, curiosity, and careful observation. It is a story of the unexpected wonders that the universe can present and the patience required to recognize and study them. Hoag's object, with its golden core, its perfect blue ring, and the hauntingly empty space in between, continues to captivate scientists and enthusiasts alike, a symbol of both the beauty and the mystery of the cosmos, a celestial riddle that began with a single, careful glance, and has persisted for more than 70 years as one of the universe's most astonishing and enigmatic creations. When most people think about galaxies, the images that come to mind are often those of majestic spirals with sweeping, curving arms unfurling gracefully from a brilliant central bulge, or large, smooth, elliptical forms that seem almost like polished cosmic marbles floating in space. These images, though beautiful, are deceptively neat. The reality of galactic structure is far messier and far more varied than these mental snapshots suggest. Spiral arms, for instance, rarely stretch out in flawless curves. Instead, they often cling together, twist, and sometimes appear jagged or fragmented, as if the galaxy were in the midst of some cosmic struggle. Elliptical galaxies, which might seem simple at first glance, can be elongated, lopsided, or clumpy, defying expectations of perfect symmetry. And ring galaxies, galaxies that, in theory, should resemble simple, glowing hoops of stars, are almost never pristine. In many cases, they are warped, bent, or broken, as though a cosmic painter had splashed colour across a canvas in a moment of improvisation. These rings can resemble ripples in a pond after several stones have been thrown in, uneven and unpredictable, rather than carefully drawn circles. It is within this context that Hoag's object emerges as something truly extraordinary. Unlike most known galaxies, this galaxy's ring is astonishingly precise. Its outer structure forms a smooth, unbroken circle of bright blue stars, creating a shape so flawless that, at first glance, it almost seems artificial. When astronomers measure the circularity of the ring, they find deviations so minuscule they are almost negligible, fractions so slight that they could be dismissed as trivial. But in the field of astronomy, such perfection is practically unheard of. The universe is inherently chaotic. Forces that govern galactic formation are unruly and unpredictable. Gravity does not act uniformly. The uneven distribution of dark matter tugs at stars in subtle, disruptive ways. Clouds of gas collapse irregularly, sometimes fragmenting, sometimes dispersing before forming stars. Even the formation of the stars themselves is an irregular process, driven by turbulence and chance. For a galactic ring to maintain such an exact, unbroken form implies that some unusual, precise mechanism is at work. To understand why Hoag's object is so unusual, it helps to look at how ring galaxies generally form. The most widely accepted scenario involves a dramatic galactic encounter. One galaxy collides with another, plunging through its center like a stone thrown into a pond. This violent intrusion generates outward-moving ripples of star formation, creating a ring-like pattern. A famous example of this phenomenon is the Cartwheel Galaxy, a sprawling, uneven wheel with bright knots of newly formed stars scattered along its arms. The ring in the cartwheel is clearly the result of a gravitational disturbance. Its asymmetries and irregularities reflect the violent event that gave it shape. But Hoag's object is fundamentally different. its ring shows none of these hallmarks of collision. There are no tidal tails, streams of gas and stars flung far into space. There are no distortions or lopsided regions where gravitational forces would have been stronger on one side than the other. Instead, the ring is remarkably uniform, with a consistent width that seems carefully measured. Even this aspect of Hoag's object is extraordinary. In many galaxies with rings, the formation of new stars tends to cluster in certain areas, creating bright regions where gas density is higher. These bright spots often make the ring appear uneven. Hoag's object's ring, however, displays a strikingly even distribution of light. Astronomers describe it as if the ring were drawn with a cosmic compass, its boundaries smooth, its brightness consistent from edge to edge. This uniformity is not merely a visual quirk, it is a precise reflection of underlying physical order. Such perfection is not just aesthetically pleasing, it is deeply puzzling. The forces that shape galaxies are inherently chaotic. Gravity pulls unpredictably in multiple directions. Gas clouds break apart or collapse in complex, seemingly random ways. Star formation is clumpy, guided as much by chance as by underlying structure. Creating a galaxy with a perfect uniform ring would be akin to watching a tempest shape a flawless sandcastle on a windswept beach. The odds seem astronomically low, yet Hoag's object defies them. Astronomers have explored several hypotheses to explain the unusual order of Hoag's object's ring. One possibility involves orbital resonance, a phenomenon in which stars and gas fall into stable, repeating patterns due to gravitational interactions. This effect is well known in our own solar system. The rings of Saturn are kept sharply defined by the gravitational influence of its moons, which act as shepherds guiding the motion of ring particles. In principle, a similar resonance could exist in a galaxy, keeping stars in a perfect ring. However, Hoag's object presents another puzzle. There are no apparent shepherds nearby. No companion galaxies, no massive neighbours close enough to exert the kind of gravitational guidance needed to sculpt the ring's perfection. The symmetry appears to arise entirely on its own. Another unusual aspect of Hoag's object is its orientation. Viewed from Earth, the ring faces almost directly toward us. In other words, we see the galaxy nearly face on, with very little tilt. This perspective is rare. Most galaxies we observe are inclined at various angles, making it difficult to view their structures in full. Statistically, observing a galaxy with such a near-perfect alignment is a matter of chance, akin to flipping a coin a dozen times and getting heads each time. That Hoag's object presents itself in such a favourable orientation makes its mysteries even more pronounced. To further understand the galaxy, astronomers have turned to computer modelling. Simulations can start with various initial conditions: a past collision with another galaxy, the influence of dark matter rings, or hypothetical orbital resonances. These models, however, have consistently failed to reproduce the perfection of Hoag's object. Rings generated in simulations are almost always slightly oval, unevenly bright, or filled with dust and irregularities. They bear the general outline of a ring but lack the flawless, consistent geometry of Hoag's object. In other words, no conventional model reproduces its perfect circle. Even more intriguing, the perfection of Hoag's object's ring extends beyond its visual appearance. Spectral analysis, the study of light emitted from different regions of the ring, reveals that the motions of its stars are also unusually regular. Orbital velocities are remarkably consistent across the entire structure. This consistency indicates that the symmetry is not just surface deep, it is embedded in the very dynamics of the galaxy. The stars are moving in harmony, tracing paths that maintain the ring's integrity, almost as if following an invisible cosmic blueprint. The implications of such uniformity are profound and, in some ways, unsettling. One possibility is that the galaxy has existed in isolation for an extraordinarily long time, long enough for its structure to stabilize without significant external disruptions. In this scenario, the stars and gas gradually settled into a state of ordered motion. However, even over millions of years, internal forces, including uneven gravitational pulls from stars and dark matter, should have introduced distortions. Another possibility is that the ring is relatively young in cosmic terms. It may have formed recently enough that external and internal forces have not yet had time to disrupt its perfect form. But if the ring is new, the question remains: what event created it? Unlike other ring galaxies, there are no apparent remnants of a collision or disturbance, no leftover evidence of the forces that sculpted the ring. The galaxy's extraordinary order has even prompted some astronomers to joke, half in jest, that Hoag's object appears almost engineered. Of course, there is no evidence of any artificial or extraterrestrial construction. The comment merely underscores how dramatically the galaxy stands out against the usual backdrop of cosmic chaos. Its near-perfect symmetry, its flawless ring, and its consistent stellar motions make Hoag's object an anomaly. In a universe where most galaxies are messy, irregular, or disrupted, it shines as an example of order that borders on the uncanny. In visual surveys, Hoag's object draws immediate attention. Its shape is arresting. The human mind instinctively recognizes the symmetry and assumes it must be special. Yet, this sense of perfection is not just an illusion. Astronomical measurements confirm that the ring's uniformity is real. Its diameter, the thickness of its ring, and the brightness distribution all align with extraordinary precision. Every measurement reinforces the sense that this is not a typical galaxy. It is in effect a cosmic puzzle, a looping circle of stars that defies expectations. The galaxy also challenges our understanding of galactic evolution. Ring galaxies typically bear the scars of their origins. Collisions leave tidal tails, uneven star distributions, and disrupted gas. Spiral galaxies show arms that twist and warp under gravitational forces. Elliptical galaxies display clumping and elongation. Hoag's object, by contrast, exhibits none of these irregularities. The forces that normally create chaos in galactic systems appear to have been either absent or perfectly balanced in this galaxy. It is a rare instance where the universe seems to have conspired to produce something not just orderly, but nearly flawless. Some scientists speculate that Hoag's object's perfection might hint at unusual physics or dynamics. Could a ring of dark matter, invisible but massive, have helped stabilize the stars into such a uniform shape? Or perhaps an unseen interaction long ago set the galaxy on a path toward this extraordinary symmetry? These questions remain unanswered. Current observational evidence is limited, and the galaxy resists easy categorization. Its characteristics challenge both theoretical models and computer simulations, leaving astronomers both baffled and fascinated. Another remarkable aspect is the color of the ring. The stars forming the loop are bright blue, indicating that they are young, massive stars. Blue stars burn intensely and live short lives, often only a few tens of millions of years before exhausting their fuel. This suggests that the ring is not only precise in shape, but also active in star formation. The stars are relatively young and tightly packed into the ring's narrow width, reinforcing the galaxy's unusual regularity. It is as if the universe arranged a temporary stage for the brilliant performance of these stars, holding them in an exact formation that few other galaxies can achieve. Astronomers also note that the interior of the ring contains a golden yellow core. This central bulge is reminiscent of older, more evolved stars, contrasting with the vibrant youth of the outer ring. The juxtaposition of an ancient core and a young, precise outer ring further underscores the galaxy's uniqueness. It is a combination that is rarely seen, with the orderly outer structure seemingly divorced from the chaos expected in galactic centers. The rarity of Hoag's object cannot be overstated. Among the billions of galaxies in the observable universe, examples with such symmetry are virtually non-existent. Surveys of nearby galaxies, both spiral and elliptical, reveal a universe dominated by irregularities. Galaxies collide, merge, and distort constantly. Even structures that seem circular or symmetrical at first glance often yield hidden complexities upon closer inspection. Hoag's object stands apart because its symmetry is not superficial. It is embedded in both its form and its motion. Its orientation, its near-perfect circularity, its uniform brightness, the consistency of stellar motion, and the vivid blue of its ring all combine to make it one of the most unusual galaxies ever observed. The galaxy forces astronomers to rethink assumptions about what is possible in cosmic structures. The simple expectation that galaxies must always bear the marks of disorder, collisions, and chaotic star formation is challenged by Hoag's object. It is a reminder that the universe can occasionally produce phenomena that defy standard explanations, requiring both new models and creative thinking. While the galaxy continues to be studied, it also captures the imagination. Images of Hoag's object are striking not just because of their scientific interest, but because of the aesthetic and almost surreal quality of the ring. To look at it is to confront an object so ordered that it seems out of place amid the general disorder of the cosmos. The galaxy's elegance draws attention, but it also raises profound questions. How did such perfection arise? How is it maintained? And what does it tell us about the forces shaping the universe? The galaxy's elegance draws attention, but it also raises profound questions. How did such perfection arise? How is it maintained? And what does it tell us about the forces shaping the universe? In the end, Hoag's object remains a cosmic enigma. It is a ring of stars so flawless, so symmetrical, that it challenges both observational astronomers and theoretical models. It is a reminder that the universe, while often chaotic and unpredictable, can occasionally create islands of astonishing order. Its ring, with its uniform brightness, consistent width, and coherent stellar motions, is not merely a visual spectacle. It is a scientific puzzle that continues to intrigue and confound. As far as we know, it is a natural phenomenon, yet its precision makes it feel almost as though it were designed. Hoag's object is a reminder that even in a universe dominated by chaos, moments of near-perfect harmony can emerge, shining brightly across hundreds of millions of light years, a cosmic loop that seems to defy the rules we thought were universal. This galaxy, more than any other, compels us to pause when we examine the heavens. Its unusual characteristics, the startling regularity of its ring, and the contrast between its young blue stars and older golden core make it a singular object in the cosmic tapestry. Scientists continue to debate its origin, test models against its properties, and speculate about the forces responsible for its existence. Yet, despite all these efforts, Hoag's object retains an aura of mystery, a rare and compelling exception to the generally chaotic patterns that govern the formation and evolution of galaxies. In a universe that is constantly evolving, colliding, and forming new structures, Hoag's object stands out as a monument to precision. Its nearly perfect circularity, the harmony of its stellar motion, the consistency of its star formation, and the almost impossibly favourable orientation from our vantage point make it one of the most fascinating astronomical discoveries of the modern era. It challenges our understanding, stretches the limits of our models, and inspires both awe and curiosity. The galaxy remains a cosmic riddle, a gleaming blue ring of stars suspended in space, reminding us that the universe is capable of producing beauty and order that, at least sometimes, seems to defy the very laws we have spent centuries trying to understand. Hoag's object is not just another galaxy, it is a symbol of the universe's capacity for surprise. While most galaxies carry the scars of time, collision and chaos, this one exhibits a rare and remarkable clarity. It is a celestial testament to the unexpected, a single, perfect ring of stars that compels us to wonder not only about how galaxies form, but about the astonishing variety of possibilities that the cosmos holds. As astronomers continue to study it, Hoag's object will remain an enduring puzzle, a vivid illustration of the extraordinary phenomena that can arise naturally in the vast and mysterious expanse of the universe. At the heart of Hoag's object lies a dense, almost perfectly round sphere of stars that glows with a deep golden light, resembling a small elliptical galaxy. Its presence is immediately striking, yet strangely understated when compared with the dazzling ring of blue stars that encircles it. While the golden core might seem secondary at first glance, it is in fact a dominant component of the galaxy's visible mass. The majority of the stars that can be seen within the galaxy are concentrated in this central sphere. Its golden hue is a telltale sign of its age. The stars at the core are ancient, having existed for billions of years, far longer than the comparatively youthful stars that make up the surrounding ring. The light that emanates from the core carries a warm, mellow tone, reminiscent of the gentle glow of stars that have long since passed through the majority of their life cycles. Elliptical galaxies, by their very nature, are collections of aged stars packed tightly into smooth, rounded shapes. They are typically born from ancient cosmic events, often from the merging of smaller galaxies long ago. These galaxies usually contain very little gas or dust, the essential ingredients for creating new stars. As a result, most elliptical galaxies are largely inactive when it comes to star formation, having long since exhausted the raw materials needed to generate new stellar generations. The core of Hoag's object aligns almost perfectly with this description, yet the stark contrast between this seemingly inert ancient heart and the vibrant electric blue ring that surrounds it is among the most perplexing features of the galaxy. Spectroscopic observations, which allow astronomers to analyze the light emitted by stars to determine their age, composition, and motion, reveal a profound difference between the core and the ring. The stars in the golden center are significantly older than those in the ring. In some instances, the age difference spans billions of years, indicating that the core predates the formation of the ring by an extraordinary margin. This finding immediately prompts a series of compelling questions. How did such a youthful, highly active ring form around an object whose central core is already so old? What cosmic processes could arrange such a perfect, bright and structured ring around a seemingly dead stellar heart? The internal structure of the core is equally fascinating. Unlike many elliptical galaxies, which often bear the scars of their tumultuous pasts, Hoag's object's core appears unnervingly smooth and unblemished. There are no winding dust lanes, no irregular clumps of gas, and no faint streaks or ripples of stars hinting at prior cosmic collisions. Most elliptical galaxies, even those that are billions of years old, reveal subtle signs of past interactions. These can appear as thin shells of stars, faint streams, or tiny ripples left behind when galaxies collided or merged. In contrast, the golden sphere at the center of Hoag's object is pristine, unmarked by such evidence. This raises another puzzling question. If the ring was the result of a collision or gravitational encounter, why does the core remain so immaculate, seemingly untouched by the violent forces that might have shaped its surroundings? Even the distribution of light within the core, the way brightness changes from its center outward, defies expectations. The light profile is more concentrated than astronomers would have predicted for a galaxy of this mass. It is as though some unseen force compressed the core long ago, yet there are no current signs of gravitational compression or disturbances from a nearby collision. One hypothesis suggests that the core might be the remnant of a small elliptical galaxy that once approached a larger spiral galaxy. The interaction may have stripped away the outer layers of the smaller galaxy, leaving only its dense inner core and triggering the formation of the ring. However, this scenario still does not fully account for the near-perfect symmetry and delicacy of the ring, which appears almost surgical in its precision. Another possibility considers the ring as the product of gas that originated in a companion galaxy, long since lost or absorbed. This gas could have been drawn into orbit around the central core, gradually forming the bright star-forming ring seen today. However, for such a scenario to occur, the gas would have needed to settle into an extraordinarily stable and uniform orbit. Achieving this level of balance in the chaotic environment of space is far more complicated in practice than it is to theorize. The golden core offers more than just visual clues. It also provides critical chemical insights. Stars in this region display a high metallicity, meaning they contain a richer abundance of heavier elements such as carbon, oxygen, and iron. This chemical richness indicates that the core has experienced multiple generations of star formation over its ancient history. Earlier generations of stars would have produced heavier elements through nuclear fusion and dispersed them into the surrounding gas, which then formed subsequent generations of stars enriched with these metals. In contrast, the stars in the surrounding ring do not share this same chemical signature, suggesting that the two structures developed in vastly different environments. It is as if the core and the ring belong to separate galactic systems that somehow came together to form a single, coherent structure. The motion of the core adds another layer of intrigue. Unlike most elliptical galaxies, which typically retain some degree of rotation from their formation, the heart of Hoag's object appears to be largely motionless. Its spin is much lower than would be expected for a galaxy of its size and age. Meanwhile, the surrounding ring rotates at a far faster pace, reinforcing the idea that the two components may have originated in completely different circumstances. The disparity between the core and ring motions implies a past in which these two systems converged and settled into a stable configuration without completely disrupting each other. Astronomers have attempted numerous simulations to reproduce such a galaxy, with varying degrees of success. Most models fail because the same processes that could feasibly create the ring A collision with another galaxy, or a close gravitational encounter, would also disturb the core. Such events typically leave visible distortions, asymmetries, or traces of shock waves, none of which are apparent in the golden center of Hoag's object. The fact that the core remains unblemished suggests either that the formation of the ring did not involve major violent interactions, or that if a disturbance did occur, it happened so far in the past that the core had sufficient time to relax and smooth out any structural irregularities. This interplay of contrasts is part of what makes Hoag's object one of the most captivating galaxies known to science. The warm golden core exudes a serene aged brilliance, while the electric blue ring radiates energy, youth, and star-forming vigour. Between them lies a dark, nearly empty gap, a boundary that accentuates the separation of the two regions while also emphasising their cohesion. This gap ensures that the two structures, despite their proximity, do not blend into one another. Instead, they exist in a careful balance, maintaining their identities while forming a visually and scientifically remarkable whole. The ring itself is a phenomenon worthy of deep study. Its stars are young, bright, and teeming with energy. The blue hue indicates active stellar formation, a stark contrast to the elderly golden stars at the centre. The gap between the core and the ring is devoid of significant matter, a vacuum of sorts, which further accentuates the separation of the two stellar populations. This spatial division is unusual in the galactic world, where most structures gradually transition from core to outskirts, blending older and younger stars more seamlessly. In Hoag's object, the separation is almost ceremonial, creating a cosmic stage where the two very different epochs of stellar life coexist but remain distinct. Theories about the ring's origin remain speculative but fascinating. It is possible that the ring formed from material that was gravitationally captured by the core long after the core had fully matured. This material could have come from another galaxy that drifted too close, or from residual gas that managed to settle into a highly stable orbit around the core. Once in place, the gas began forming stars, creating a spectacularly bright and structured ring. Another theory suggests that the core itself may have influenced the ring's formation, its gravitational field acting as a sculptor, gently guiding the infalling material into a circular, orderly orbit. Whatever the exact mechanism, the precision of the ring's structure remains one of the most extraordinary aspects of Hoag's object. The pristine condition of the core, combined with the orderly elegance of the ring, makes this galaxy a kind of cosmic paradox. It challenges the conventional understanding of how galaxies evolve. In most cases, when galaxies interact, collide, or merge, the aftermath is chaotic and violent, leaving behind distorted shapes, scattered stars, and turbulent gas clouds. Yet here, in this remote corner of the universe, the golden core remains untouched, while the surrounding ring has formed with a strikingly perfect geometry. It is a rare example of order emerging from what is normally a universe defined by disorder. The chemical evidence reinforces the distinctiveness of the core and ring. The higher concentration of heavy elements in the core points to a long history of star formation that occurred in multiple waves over billions of years. Each generation of stars contributed to the enrichment of the gas, creating a progressively heavier elemental mix. In contrast, the blue ring displays a much lower metallicity, indicative of younger stars that formed in a chemically simpler environment. This disparity further supports the notion that the core and ring have separate origins, converging later to form a unified galaxy without erasing the individual histories of either component. The motion, or relative lack thereof, of the core is yet another clue to its unusual nature. In most elliptical galaxies, even those billions of years old, stars retain a faint rotational motion from the galaxy's initial formation. In Hoag's object, the core exhibits almost no rotation, suggesting that it has settled into a highly stable, static state. The surrounding ring, by contrast, rotates rapidly, with stars moving along defined orbits. This juxtaposition of a static inner core and a dynamic outer ring indicates that the two components did not form together in a conventional manner. They may have originated in entirely separate systems and later merged in a manner that allowed them to coexist without significant disruption. Astronomers continue to explore models that could explain how such a galaxy could form. One possibility is that the core formed first, billions of years ago, as a small elliptical galaxy. Later, it may have acquired the material that would become the ring, either through the capture of a gas-rich galaxy or from material expelled by nearby cosmic events. Over time, this material settled into a stable orbit around the core, forming stars in a precisely arranged ring. The smoothness of the core suggests that any violent events that may have accompanied the ring's formation were either minor or occurred so long ago that the core had time to regain equilibrium. The visual contrast between the golden core and the vivid blue ring is what makes Hoag's object one of the most striking galaxies known. The core emits a gentle, warm light, a testament to its ancient stars and long history, while the surrounding ring glows with energetic brilliance, signifying ongoing stellar birth. Between the two lies a dark, empty gap, emphasizing the separation, yet highlighting the harmony between the two structures. This extraordinary arrangement creates a galaxy that is not only scientifically intriguing but also aesthetically remarkable, a rare celestial jewel that challenges our understanding of galactic formation and evolution. Hoag's object exemplifies a cosmic duality. The ancient and the young, the calm and the active, the dense and the expansive, all coexisting in one coherent structure. The core and the ring are almost like two separate galaxies that have found a way to exist in mutual balance. The golden heart remains untouched by time and cosmic violence, while the electric blue ring continues to shine brightly with youthful vigor. The space between them is a testament to the subtle forces that maintain their separation and stability, ensuring that the galaxy remains a coherent, yet paradoxical whole. In summary, the galaxy known as Hoag's object challenges nearly every conventional idea about galactic formation. Its dense, golden core is ancient, chemically enriched, smooth, and nearly motionless. Its surrounding ring is young, vibrant, blue, and full of active star formation. The separation between the two is distinct, yet they form a single, breathtakingly beautiful galaxy. The origins of the ring remain a mystery, with theories ranging from gravitational capture to residual gas settling into orbit, but none completely explain the pristine condition of the core. The juxtaposition of age and youth, of calm and activity, creates a galaxy that is as scientifically puzzling as it is visually stunning. Hoag's object stands as one of the most elegant and enigmatic structures in the observable universe, a cosmic masterpiece where two very different epochs of stellar history coexist in perfect harmony, separated by a mysterious, almost ceremonious gap of empty space. In the vast expanse of the cosmos, Hoag's object stands out as one of the strangest and most mesmerizing galaxies ever observed. Its allure is not only in what it contains, but, perhaps more importantly, in what it seems to be missing. When astronomers look at it, one of the first things that strikes them is the enormous, eerie emptiness that separates its glowing golden center from its luminous outer ring of blue stars. This is not a small void. It stretches across tens of thousands of light years, a vast cosmic gulf that seems almost deliberately placed between the two brightest regions of the galaxy. In the study of galaxies, astronomers are accustomed to seeing regions filled with stars, gas clouds, and sometimes faint interstellar dust even between the most prominent features. Spiral galaxies, elliptical galaxies, and even ring galaxies that form after violent cosmic collisions usually have at least some scattered stars, faint wisps of gas, or lingering remnants of the chaotic events that shaped them. Yet in Hoag's object, this middle space, this bridge between core and ring, is almost startlingly empty. From the earliest detailed images taken by the Hubble Space Telescope, scientists were surprised by how clean and unpopulated this area is. It is not just that there are no bright young stars blazing against the void, even older, dimmer stars are practically absent. This gap is not an illusion caused by the limits of our telescopes. Deep Hubble images, which can pick up even very faint stars, confirm that this emptiness is real. It is as if some invisible hand has swept the space clean, leaving behind a void that is almost surgical in its precision. Compared to other ring galaxies, Hoag's object is profoundly unusual. In galaxies formed through collisions, like the famous Cartwheel Galaxy, the space between the central core and the outer ring is rarely quiet. There, one finds streams of stars flung outward by the violent gravitational interactions that created the ring. Clouds of gas swirl in turbulence, clumps of matter drift about unpredictably, and regions of ongoing star formation light up the interior with scattered bursts of brilliance. In other words, there is chaos and clutter in the gaps of most galaxies, a messiness that reflects the complexity of the forces that shape them. Hoag's object, however, is almost the opposite. Its gap is stark, clear, and sharply defined, as if some cosmic law has drawn a boundary that prevents the inner core and outer ring from mingling or influencing each other in the usual ways. Understanding why this gap exists has puzzled astronomers for decades. One theory involves orbital mechanics, the idea that the motions of the stars and gas in the ring might naturally avoid the inner region. In many ways, this is similar to the way the moons of Saturn maintain gaps in the planet's rings. These moons exert gravitational influence on the ring material, keeping some areas free of debris and creating the distinctive divisions that make Saturn's ring so striking. Could something similar be happening in Hoag's object? Perhaps the stars in the ring are moving in such carefully balanced, almost synchronous orbits that they never stray into the void. If so, the gap would be a naturally stabilized feature, maintained by the subtle gravitational forces at work in the galaxy. But here the analogy falters. In Saturn's rings, the moons are visible, clear objects whose influence can be measured. In Hoag's object, there is no such guardian. There are no observable stars, clusters, or massive bodies in the void that could account for the sharp separation. The gap appears to exist on its own, without any visible agent maintaining it. Another possibility is that the emptiness was created by a dramatic event in the galaxy's distant past. A massive outburst of energy from the central core could have pushed gas outward, preventing new stars from forming in the interior region. Perhaps a supermassive black hole at the heart of the galaxy erupted with a tremendous release of energy hundreds of millions of years ago, blasting away the raw material needed to form stars. Over time, without fresh gas to collapse into new stars, the void would have remained barren, a silent zone separating the two luminous regions. While this idea is intriguing, it too raises questions. Observations today do not show evidence of a powerful active black hole at the center of Hoag's object. The core is not radiating intense energy, there are no observable jets of high-energy particles, and there are no unusual X-ray emissions that would indicate the presence of a currently active black hole. The theory, therefore, can explain the emptiness only if the activity occurred in the remote past, long enough ago for the galaxy to settle into its present state. Chemical analyses of the few stars that do exist in the gap add further layers to the mystery. The stars that are detectable here are chemically distinct from both the golden core and the blue ring. Their elemental composition suggests that they are relics from an earlier stage of the galaxy's history, perhaps survivors from a time before the ring formed. This raises profound questions about the galaxy's past. Could Hoag's object have begun life as a completely different kind of galaxy, only to be transformed over cosmic time into the extraordinary structure we see today? The empty space might be a fossil, a preserved zone that remembers the galaxy's previous identity, holding traces of an earlier arrangement of stars and gas that has otherwise vanished from view. The emptiness also presents a fascinating gravitational puzzle. Both the core and the ring exert gravitational forces on each other, tugging and pulling at stars and gas over millions of years. In most galaxies, such forces eventually cause matter to drift, filling gaps and smoothing transitions between different regions. One would expect the void between the core and the ring to gradually become populated, a slow mixing process of stars and gas that erases sharp boundaries. In Hoag's object, however, the gap remains remarkably well defined. Any model that attempts to simulate this stability requires extremely finely tuned conditions, precise balances that seem unlikely to occur and persist naturally over hundreds of millions of years. The consistency of the gap, then, is not just unusual, it is extraordinary, defying the normal expectations of galactic evolution. Visually, the emptiness contributes significantly to the galaxy's otherworldly appearance. The golden core does not gradually fade into the blue ring surrounding it. Instead, there is a near-perfect, almost surgical demarcation between the two regions. This sharpness creates the impression that the galaxy is meticulously constructed, with a precision that seems almost deliberate. It is important to note that no astronomer has suggested that Hoag's object is artificial, and there is no evidence to support such a notion. Yet the visual effect is striking. In a universe usually governed by chaos, collisions, and random distribution, The clarity of the gap is unsettling. It speaks in silence, a loud absence in the language of the cosmos, emphasizing what is not there with the same intensity as what is. This absence complicates our understanding of galactic dynamics and formation. If the core and the ring have distinct histories, originating at different times or from separate processes, then the void could be a sign of a union that is essentially permanent. It is a place where stars and matter have failed to settle for hundreds of millions of years, a gravitational neutral zone where the usual rules of star formation and motion do not apply. Even the most powerful telescopes available today cannot fully resolve what might exist within the void. There may be faint streams of dark matter, invisible to our instruments, subtly shaping the region without producing light. Alternatively, it could be a gravitational dead zone, a portion of the galaxy where the density of gas is too low, the conditions too hostile for new stars to form. Whatever the explanation, the empty gap is as defining a characteristic of Hoag's object as the golden core or the radiant blue ring. It is a mystery in negative space, a phenomenon that challenges astronomers' understanding of how galaxies form, evolve, and maintain their shapes over cosmic time. By studying this emptiness, scientists gain a glimpse into forces and histories that are not immediately apparent, revealing how subtle gravitational influences, chemical histories, and perhaps ancient cosmic events can shape the structure of an entire galaxy. It is a reminder that the universe is not only made of light and matter, but also of absence and voids, and that sometimes the most profound mysteries lie in what is not there, in the spaces between the stars. In thinking about this gap, one can almost feel the patience of the cosmos. While stars are born, live, and die, and galaxies collide and merge in spectacular displays of energy, this void remains untouched, unoccupied, a stable emptiness that persists for eons. It is a testimony to forces we do not yet fully understand, to processes that may involve the careful orchestration of gravitational mechanics, chemical evolution, and ancient cosmic events that are impossible to witness directly. The few stars that exist within it, fossils of a previous era, hint at a history that predates the galaxy's current form, suggesting that Hoag's object is not a static object, but a palimpsest, a record of multiple epochs of cosmic evolution written in the language of stars and emptiness. Ultimately, the empty space between the golden core and the blue ring of Hoag's object transforms the galaxy from a mere visual curiosity into a profound cosmic puzzle. The gap is not a flaw or an accident. It is a fundamental feature, one that defines the galaxy's identity and challenges our assumptions about the universe. In a galaxy where everything seems improbably ordered, the emptiness is both a presence and an absence, a silent, eloquent statement that in space, as in life, what is missing can be just as revealing as what is seen. To study Hoag's object is to study the interplay of light and dark, presence and void, matter and nothingness. It forces astronomers to question the processes that create galaxies, to consider mechanisms beyond simple collisions or mergers, and to explore the role of invisible forces, past cataclysms, and long-forgotten histories that continue to shape the universe in subtle, almost imperceptible ways. Every telescope image, every spectrographic analysis, every orbital simulation brings new insights, yet the core mystery, the haunting emptiness, remains. It is a bridge that is not a bridge, a space that is not a space, a reminder that the cosmos is far stranger than our minds can easily grasp. In the end, the empty gap in Hoag's object is more than just a feature of a galaxy. It is a symbol of the unknown, a negative space that defines form as much as light defines shadow. It reminds us that the universe is not simply a collection of stars, gas, and dust, but also of silences, absences, and voids that hold their own stories. And as we peer into the void, seeking to understand its origins and maintenance, we are drawn into a deeper appreciation of the complexity, precision, and subtle beauty of the cosmos itself. This emptiness, this wide, dark bridge between the two brilliant regions of Hoag's object, is a mystery in the purest sense, a cosmic question mark suspended 600 million light-years away, waiting patiently for us to understand its story. It is a story that challenges our expectations, confounds our models, and stretches the imagination. It is a silent void that speaks volumes about the past, the present, and perhaps the future of the galaxy. It is an emptiness that is alive with possibilities, hinting at ancient forces, delicate balances, and invisible structures that hold the galaxy together. In Hoag's object, the gap is not simply an absence, it is a defining presence, a region of negative space that shapes the galaxy's identity, and a profound reminder that the universe often communicates in the language of what is not there as much as in what is. And so, as astronomers continue to study this extraordinary galaxy, they do so not only to map its stars and rings, but to understand the emptiness that separates them. They peer into the dark, measure the subtle gravitational pulls, analyze the few ancient stars that linger, and simulate cosmic motions that could maintain such a pristine void. Every observation reinforces the central truth. The gap is as mysterious, as essential, and as remarkable as the luminous structures it separates. It is a space that refuses to be filled, a silence that demands attention, a cosmic riddle that remains one of the universe's most beautiful and perplexing enigmas. In Hoag's object, the emptiness is not a flaw but a feature. It is not an absence to be ignored but a presence to be studied, a central character in the story of a galaxy that defies expectation and challenges understanding. The void is a moat around the golden heart, a fence around the blue ring, a negative sculpture carved across tens of thousands of light years, and in its stark, almost impossible clarity, it teaches us that the cosmos has a way of surprising us with both what it shows and what it hides. In a universe often dominated by light and matter, Hoag's object is a reminder that absence itself can be profound, a negative space that is both mysterious and essential. The gap between the core and the ring is a defining feature, a silent testament to the forces of gravity, the remnants of ancient structures, and the ongoing evolution of galaxies in ways we're only beginning to understand. It is a negative space that holds a positive significance, shaping the galaxy as much as the stars themselves, and ensuring that Hoag's object remains one of the most enigmatic and captivating objects ever discovered in the night sky. The bright blue ring surrounding Hoag's object is not merely a beautiful cosmic decoration, it is a mystery, a puzzle that seems to float around the heart of a galaxy, a riddle waiting to be solved. In the vastness of the universe, rings of stars are rare. They are unusual structures, often born from dramatic events, or the slow, precise influence of gravity. When astronomers do find them, nearly every ring tells a story. There is usually a clear origin, a series of events that shaped it, leaving behind a trail of evidence that can be traced like footprints in the cosmic dust. But Hoag's object refuses to fit into any of the patterns astronomers know so well. It resists explanation, and the deeper scientists look, the stranger it becomes. Most rings that we know about are born of violence. They are the aftermath of colossal collisions. Picture a smaller galaxy smashing into the disk of a larger one. When this happens, the encounter sends ripples outward, waves of dust and stars surging from the center, compressing clouds of gas, igniting bursts of star formation in patterns that spread like ripples in a pond. These are called collisional rings, and they are among the most studied of all cosmic rings because their formation is violent, energetic, and, importantly, traceable. Collisional rings are messy. They carry the scars of the encounter. There is debris scattered across the galactic neighborhood, remnants of the smaller galaxy that made the plunge. Their thickness is uneven, their edges ragged, and often, if astronomers look carefully, they can find the remnant or invader that caused the disruption, still lingering in the vicinity of the ring. When astronomers first encountered Hoag's object, they naturally tried to see if it could be explained in the same way. Could this ring be the product of a cosmic collision? Could it be the result of another galaxy having plunged through its heart, compressing the gas in the process and forming the spectacular circle of stars that now glows with an intense blue light? At first, it seemed a possibility. After all, the physics of collisional rings is well understood, and the outcomes are often strikingly similar to what one sees here. But when they examined Hoag's object more closely, the usual signs of a collision were absent. There was no scattered debris, there were no uneven layers of stars. The ring itself was uniform, its width consistent all the way around, like a celestial hoop that had been measured and placed with care. And perhaps most puzzling of all, there was no nearby galaxy to claim responsibility, no wandering intruder that could have caused such a perfect structure. In this respect, Hoag's object was unlike anything astronomers had ever seen. It was clean, precise, elegant, and stubbornly resistant to the collisional explanation. When the collisional model failed to fit, scientists turned to another, more subtle mechanism known to produce rings in galaxies: resonances. In many spiral galaxies, stars and clouds of gas move in response to the gravitational pull of the galaxy's structure. Often, the presence of a bar, a straight, elongated region of stars stretching through the center of a spiral, creates resonances, orbital patterns that trap matter at certain distances. Over millions of years, these resonances can accumulate stars and gas in a ring, producing beautiful, orderly formations. This is a slower, quieter process than a collision, one driven by the patient, invisible hand of gravity rather than the chaos of impact. Could Hoag's object be a resonance ring? Again, the galaxy presented obstacles. Resonance rings rely on a central bar or at least spiral arms, yet Hoag's object has neither. Its core is an elliptical structure, smooth and rounded, lacking the disc-like formations that could create the resonances needed to shape a ring. There is no mechanism to trap stars in the circular pattern seen in the blue ring. The usual gravitational choreography is missing, leaving the ring's formation mysterious and unexplained. In search of answers, astronomers considered another idea, that the ring formed not from dramatic events, but from the slow gathering of material from the surrounding cosmos. In what is known as the cold accretion model, streams of intergalactic gas gradually spiral toward a galaxy, settling into orbit far from the center. Over time, this gas cools, condenses, and begins forming stars, potentially creating a disk or ring that appears without any collision or obvious disturbance. This process can take hundreds of millions or even billions of years, and it could explain why there are no nearby galactic culprits in Hoag's object. The galaxy could simply have been patiently drawing in material from its surroundings. Yet even this model struggles to explain the ring's perfection. Gas clouds in space are rarely cooperative. They twist, warp, and form clumps, creating irregular patterns rather than smooth, uniform circles. For Hoag's object to have a ring so evenly shaped, the infalling gas would have had to organize itself with an almost impossible precision, forming stars in a flawlessly symmetrical hoop. The odds of such an outcome occurring naturally are so low that the universe almost seems to have paused to let it happen. Some scientists have even turned their attention to something far more mysterious: dark matter. Every galaxy is thought to sit inside a halo of dark matter, an invisible substance that exerts gravity but does not emit light. If a dark matter halo is particularly smooth and spherical, it could in theory guide gas and stars along paths that encourage the formation of circular structures. Perhaps the uniformity of Hoag's object's ring is the silent work of dark matter, shaping its surroundings in ways we cannot directly observe. But this theory, while intriguing, remains unproven. Dark matter cannot be seen directly, and its precise distribution around Hoag's object is unknown. Scientists can only infer its presence from the motions of stars and gas, and even then, there is no evidence to suggest that the halo of Hoag's object is unusually different from that of other galaxies. The differences in age between the stars in the core and those in the ring add yet another layer of mystery. Observations show that the golden stars in the core are ancient, formed billions of years ago, while the blue stars in the ring are comparatively young. This suggests that the ring is a later addition to the galaxy, not something that emerged alongside the core in the galaxy's earliest days. In terms of timing, this is a difficult puzzle. If a collision were responsible, it would have to have occurred at just the right moment, recent enough that the ring's stars still appear youthful, yet long enough ago for the stars to settle into the serene, almost sculpted circle that astronomers now observe. Further adding to the puzzle, the stars in the ring move in an unusual manner. Spectroscopic studies, which measure the light emitted by stars to understand their speed and direction, reveal a remarkable order. The stars orbit the core in a consistent, harmonious fashion, following nearly identical circular paths. Their motions show little of the chaotic scattering usually expected in a ring born of turbulence, whether from collision or other dynamic events. In known examples of ring formation, even after hundreds of millions of years, some level of disorder persists. Stars jostle and drift, their velocities varying from one to the next. Yet in Hoag's object, the ring appears calm and mature, as if each star has been carefully placed into position. moving in concert with its neighbours in an elegant cosmic dance. Faced with these anomalies, some researchers have ventured beyond the familiar explanations and explored more speculative ideas. One suggestion is that Hoag's object could be the result of an extremely gentle merger. In this scenario, a small galaxy might have been absorbed gradually, so slowly and evenly that it left no chaotic traces, no debris scattered like breadcrumbs across space. Its stars and gas could have been added directly to the ring, forming a stable, uniform structure without the usual scars of violent interaction. While this idea could account for some of the ring's unusual properties, it is difficult to verify, and the scenario is hard to reconcile with the precise motions and timing required. Another, even more speculative notion involves gravitational waves, ripples in the fabric of space-time caused by massive cosmic events. Perhaps, some suggest, a distant event in the galaxy's past sent out waves that compressed gas into a spherical shell around the core, triggering star formation in just the right pattern to create the ring. This remains purely hypothetical, without observational support, yet it highlights how extraordinary Hoag's object is. It challenges scientists to think in ways that stretch beyond the conventional models, to consider processes that are at the very edge of current understanding. Each theory brings pieces of the puzzle into focus, yet none fully explains the mystery. Collisions provide insight into how rings can form, yet they fail to account for the ring's unbroken symmetry and the absence of nearby culprits. Resonances offer an orderly mechanism for shaping stars, but they require a bar or disk that Hoag's object simply does not possess. Cold accretion from intergalactic gas could explain the lack of collision evidence, but it struggles to justify the ring's perfection and precise motion. Dark matter could provide guidance unseen, but its role remains speculative, and the precise properties of the halo are unknown. The more astronomers study Hoag's object, the more questions arise. Why is the ring so uniform? Why is the core smooth and elliptical, lacking the bar that would generate resonances? Why are the stars in the ring young while the core stars are ancient? How did the ring stars come to move with such precision and order? Each answer seems to reveal new mysteries, and the galaxy remains a riddle wrapped in a circle of brilliant blue light. This cosmic enigma is one of the reasons Hoag's object continues to captivate astronomers and stargazers alike. It is a reminder that the universe does not always follow the rules we think we understand. For centuries, astronomers have catalogued galaxies, noting their spirals, ellipses, and irregular forms, learning to expect certain patterns based on how gravity, collisions, and time shape the cosmos. Yet here, floating 600 million light-years away, is a galaxy that defies expectations. Its core is a smooth golden orb, calm and ancient, untouched by visible disturbance. Its ring is a flawless band of young blue stars, moving with remarkable order in a structure that is as mathematically improbable as it is visually stunning. Hoag's object is a cosmic paradox. It is a reminder that even in a universe governed by laws of physics, nature can produce outcomes that appear intentional, as if the stars themselves were arranged with design in mind. It is not merely a ring, it is a story of mystery, symmetry, and timing that challenges astronomers to rethink how galaxies evolve, how stars are born, and how unseen forces, whether dark matter, gentle mergers, or processes yet unknown, shape the heavens. The galaxy invites questions as much as it demands answers, pushing the limits of human understanding and daring us to look deeper into the cosmos for clues. Some researchers speculate that perhaps no single mechanism is responsible. Perhaps the ring is the result of multiple processes layered over eons, a combination of subtle gravitational nudges, careful accretion of gas, and the slow, invisible hand of dark matter guiding the stars into place. Perhaps its calm, orderly motions are the result of billions of years of quiet evolution, smoothing out the rough edges and leaving only the pristine form we see today. Whatever the cause, Hoag's object remains unique, a one-of-a-kind marvel in the night sky, demonstrating that the universe has surprises that can defy logic and expectation, reminding astronomers that even in the vast expanse of known galaxies, mystery endures. And yet, for all its mystery, Hoag's object is more than a scientific curiosity. It is a symbol of cosmic beauty, a jewel suspended in the dark expanse, a reminder that the universe is not always chaotic, nor always violent. Sometimes it can be breathtakingly orderly, astonishingly precise and quietly perfect. The blue ring is not merely a ring of young stars, it is a challenge, a riddle, a story written in light and gravity, spanning hundreds of thousands of light years, whispering to astronomers and dreamers alike that there is still so much we do not know, that even in the vast emptiness of space, the universe has the capacity to surprise and to inspire. No other galaxy quite resembles Hoag's object. Its combination of an ancient golden core and a perfectly uniform blue ring is unlike the aftermath of any known collision, unlike the product of any resonance pattern, unlike the result of ordinary accretion or star formation. Every observation adds layers of complexity. Every model tested falls short in some way. The more scientists explore, the more the galaxy resists conventional explanation. Its very existence forces a reconsideration of the rules of galactic formation, challenging assumptions about how stars arrange themselves, how rings can form, and how cosmic structures can maintain such perfect symmetry over unimaginable spans of time. The enigma of Hoag's object continues to baffle astronomers and astrophysicists, standing as one of the most confounding puzzles in the study of galaxies beyond our own Milky Way. From a distance of approximately 600 million light-years, it gleams like a jewel suspended in the darkness of the cosmos, a bright golden core encased in a perfect luminous ring of young blue stars, separated by a vast, hauntingly empty gap. At first glance, it might appear simply as a rare cosmic beauty, a galaxy that delights the eye with its symmetry and elegance. But upon closer examination, it becomes immediately apparent that this galaxy refuses to conform to the rules and models that astronomers have painstakingly developed over decades of observing the universe. Every attempt to explain it using familiar concepts seems to falter, leaving more questions than answers. One idea that initially seems promising is the concept of gas accretion. This process, which involves a galaxy gradually pulling in gas from its surroundings, could potentially explain why the stars in the ring of Hoag's object are so young. Fresh gas can collapse under its own gravity, forming new stars in regions where old stars are not abundant. In theory, this could account for the bright blue ring that encircles the central golden sphere. Yet, while gas accretion can explain the youth of the stars, it fails to explain something equally puzzling: the absence of any discernible patterns or irregularities in the structure. If the ring had been formed through a conventional process of star formation fed by accreted gas, one might expect to see clumps, spirals, or arcs of stars indicating regions of more intense activity, much like the star-forming regions observed in other galaxies. Instead, Hoag's object presents an almost eerily uniform and symmetric ring, as though some unseen hand meticulously placed each star in perfect order. Another popular hypothesis involves dark matter, the mysterious invisible substance that is believed to make up a significant portion of the universe's mass. Some scientists have speculated that a ring of dark matter could be influencing the formation of the stars in the outer ring, guiding gas and dust into a circular structure that then forms stars. But this idea, too, remains without proof. Despite advances in observational technology and simulations, there is no concrete evidence that a dark matter ring exists around Hoag's object. It remains an intriguing suggestion, but it cannot yet serve as a definitive explanation. In truth, the formation of Hoag's object resists all conventional classification. It occupies a quiet, almost lonely region of space, and its structure seems to defy every expectation, presenting itself with features that simply should not exist according to known models. In most cases where astronomers observe a galaxy shaped like a ring, their first assumption is that it was created by a collision, a catastrophic interaction with another galaxy. The majority of ring galaxies we have documented appear to owe their form to a dramatic crash, a cosmic collision in which a smaller galaxy ploughed directly into the disk of a larger one. The physics of such encounters are well understood. When a smaller galaxy intrudes, it sends ripples through the larger galaxy's disk, waves of stars and gas that propagate outward in the shape of a ring. These waves compress the interstellar gas, triggering new bursts of star formation that light up the ring with brilliant blue stars. This scenario has been observed multiple times, with the Cartwheel Galaxy standing as the most famous example. Its ring is irregular, patchy, and surrounded by wisps of stars and clouds of gas, all of which bear the unmistakable signature of a violent past. The irregularity, the scattered debris, the tidal tails, and the chaotic distribution of material are all evidence of the forces unleashed during a galactic collision. But when astronomers focused on Hoag's object, they found that the usual collision model simply did not fit. The galaxy lacks every obvious clue that would suggest a recent or even ancient impact. The first striking observation is the absence of debris. In a typical galactic collision, the gravitational forces at play are immense. They fling stars, gas, and dust outward, creating long, faint streams called tidal tails, arcs of material, and distorted shapes that extend far from the core. Hoag's object, however, appears exceptionally clean. There are no tails, no arcs, no messy knots of gas drifting away from the ring. The space surrounding it is unusually pristine, an empty void with nothing flung outward to hint at a violent past. The lack of these features suggests two possibilities. Either no collision ever occurred, or if it did, it happened so long ago that every trace has vanished. Yet this latter option presents a contradiction, for the ring's stars are astonishingly young. The bright blue hue of the stars indicates ages of only a few 100 million years, a mere blink in cosmic terms, making it improbable that an ancient collision could account for the ring's current appearance. The second inconsistency is the absence of an intruder galaxy. In almost all known ring galaxy systems formed by collisions, the galaxy responsible for the crash, often called the intruder, can still be found nearby, either slowly merging with the central galaxy or lingering in the vicinity. Yet Hoag's object exists in isolation. The nearest sizable galaxies are far too distant to have been involved in any recent collision. Deep sky surveys, which map the faintest objects across vast distances, have not revealed even a small remnant that could have been the shredded remains of an absorbed intruder. The expected signatures of a galactic interloper, such as distorted stellar motion or lingering material from the collision, are nowhere to be found. The third anomaly lies in the ring's near-perfect symmetry. Collisions, by their very nature, are messy. Rarely does a smaller galaxy strike exactly at the centre of another. Any slight offset, even a fraction of a degree, typically produces a lopsided or irregular ring, sometimes elliptical, sometimes fragmented. Hoag's object defies this expectation. Its ring is almost mathematically circular, as if it were drawn with a compass by an invisible artist. If the ring were the result of a collision, it would have required an extraordinarily precise impact, aligned so perfectly that the odds are almost laughable. Imagine trying to fire an arrow across an entire football field and hitting the exact bullseye of a target that is moving at high speed. That is the level of precision needed to create Hoag's object through a conventional crash. Velocity measurements introduce yet another complication. In galaxies formed by collisions, the stars and gas in the ring generally display a wide range of velocities, a chaotic pattern that reflects the residual energy from the violent interaction. Hoag's object, by contrast, exhibits a remarkably uniform rotation in its ring, suggesting a level of stability that is difficult to reconcile with the idea of a fresh collision. For the stars and gas to have settled into such perfect rotational order, the system would either need to achieve an unprecedented degree of equilibrium in a remarkably short span of time, or the ring was never formed by a violent encounter at all. Some scientists have attempted to salvage the collision hypothesis by proposing more exotic scenarios. One suggestion is the ghost intruder theory, where a very small gas-filled galaxy might have collided with Hoag's object in such a way that it merged seamlessly into the outer ring without leaving any visible signature. Even this theory, however, faces serious challenges. A gas-rich intruder, no matter how small, should leave detectable gravitational imprints such as distortions in the movement of stars within the central core. Yet the core of Hoag's object appears remarkably unaltered, exhibiting no irregularities that would betray such an event. Another variant of the collision theory involves the possibility of a massive gas cloud striking the galaxy rather than another galaxy. Theoretically, a collision with a large, diffuse cloud of gas could trigger the formation of a ring without producing the usual chaotic debris. But this idea raises additional questions. Where is this gas cloud now, and how could it have distributed material so evenly to create a ring of such flawless symmetry? Observations show no evidence of a substantial gas reservoir lingering near Hoag's object, leaving this hypothesis incomplete at best. Due to these inconsistencies, many astronomers hesitate to classify Hoag's object alongside more familiar ring galaxies like the Cartwheel. Its appearance, behaviour, and surrounding environment all differ in ways that are profound and perplexing. While the Cartwheel and similar galaxies provide clear visual testimony of violent formation histories, Hoag's object presents a quiet, almost serene contrast. It rotates smoothly, its ring is intact and undisturbed, and its central core remains untouched. It behaves in a way that seems deliberately designed to confound conventional classification. If the collision model cannot explain Hoag's object, we are left with two possibilities, both of which are profoundly intriguing. The first is that astronomers have simply overlooked some critical aspect of galaxy formation. Perhaps there are processes at work in the universe that we have yet to observe or understand, mechanisms capable of producing a ring of young stars with such symmetry and stability without leaving behind debris or irregular motion. The second possibility is even more tantalizing. Hoag's object may represent an entirely new mode of galactic evolution, one that is fundamentally different from the processes we have long relied upon to explain cosmic structures. In this case, the galaxy is not merely unusual, it is a window into a set of phenomena that could redefine our understanding of how galaxies form, evolve, and interact with their environments. The mystery deepens when we consider the environment in which Hoag's object exists. Unlike many galaxies that inhabit dense clusters or groups, Hoag's object is relatively isolated. Its location in a quieter region of space might contribute to its unusual properties. Without nearby neighbours to perturb it gravitationally, the galaxy could maintain an equilibrium that is impossible for more crowded systems. Yet isolation alone does not explain the existence of the perfectly circular ring or the youthful stellar population. These features suggest an active formation process rather than mere survival. Astronomers also turn to detailed spectroscopy and imaging to probe the internal dynamics of Hoag's object. Observations have confirmed that the stars in the ring follow a coherent rotation pattern, almost as if choreographed. The central core, composed primarily of older golden stars, shows no signs of recent disruption or inflow of material that would be expected if a collision had occurred. Furthermore, the gap between the core and the ring is vast, spanning tens of thousands of light years, and curiously empty of stars. This space is not merely a void in brightness, it is genuinely sparse in stellar content, highlighting a dramatic discontinuity between the central core and the ring. The galaxy appears to have formed its two major components independently, a scenario that defies most standard models. Some speculative theories attempt to reconcile these observations by invoking processes beyond traditional galaxy formation. One idea is that interactions with dark matter, though unobservable, could subtly shape the distribution of stars and gas to form such a ring. Another is that some unknown resonance in the galaxy's gravitational field could shepherd gas into the outer ring, triggering star formation without producing chaos. These ideas remain highly tentative, lacking definitive evidence, but they reflect the lengths to which scientists must go to make sense of Hoag's object. Each hypothesis underscores the fact that this galaxy refuses to fit neatly into our current understanding. The enduring allure of Hoag's object lies not just in its appearance, but in its ability to challenge assumptions. It reminds astronomers that the universe is far more inventive than our theories often anticipate. A galaxy can exist that looks ordered and simple at first glance, yet hides profound mysteries beneath its serene exterior. It demonstrates that cosmic evolution is not always messy and violent. Sometimes, it can produce structures of astonishing regularity and elegance. Yet even elegance does not equal simplicity. The galaxy's formation history, the origin of its ring, and the reasons for its isolation remain open questions, invitations to curiosity and further study. What makes Hoag's object one of the most fascinating and mysterious galaxies in the universe is not only the flawless symmetry of its bright ring, or the unusual, almost perfectly spherical core at its centre, but also the fact that it resides in an extraordinarily empty and lonely region of space. While most galaxies are social creatures in the grand cosmic sense, Hoag's object appears to have chosen, or perhaps simply been born into, a life of solitude, far removed from the bustling communities where galaxies usually interact, collide, and evolve. Galaxies, in the majority of cases, are far from isolated. They form clusters, associations, and groups, bound together by the invisible but ever-present pull of gravity. These groups can contain dozens, hundreds, or even thousands of galaxies, all tugging and nudging at one another, sharing interstellar gas, and occasionally crashing together in spectacular cosmic collisions. Such interactions are messy, chaotic, and sometimes violent, but they are also the engine of galactic transformation. Through these encounters, galaxies change their shapes, trigger waves of star formation, feed the supermassive black holes at their centers, and redistribute the gas and dust that fuel their ongoing evolution. The gravitational dance of galaxies is, in a sense, what keeps the universe alive and dynamic. Hoag's object, however, seems to have been excluded from this cosmic crowd. When astronomers chart its surroundings, mapping the positions of nearby galaxies and tracing the web of matter that permeates space, they are met with a startling emptiness. Its immediate neighbourhood is almost eerily devoid of substantial companions. The nearest galaxies of comparable size or mass are millions of light-years away, far too distant to exert any meaningful gravitational influence on Hoag's object. In human terms, if most galaxies live in the crowded, noisy cities of the cosmos, Hoag's object resides deep in the rural countryside, surrounded by vast expanses of emptiness, broken only by faint, dimly glowing galaxies scattered across the distant background. This solitude, while poetic, is also deeply consequential. The fact that Hoag's object is so isolated removes many of the usual triggers that can radically alter a galaxy's appearance over cosmic time. In dense regions of the universe, galaxies are in a near-constant state of disturbance. They are tugged by tidal forces from neighbours, stripped of gas through gravitational harassment, or sent spinning and twisting by close encounters with other massive objects. Collisions can funnel clouds of gas toward the galactic centre, fueling starbursts and feeding central black holes, while mergers can dramatically reshape a galaxy, turning a spiral into an elliptical, or producing long tails of stars and gas stretching across space. In contrast, Hoag's object lives without such disturbances. Its isolation may be the reason its magnificent ring has survived intact, perfectly circular, for millions or even billions of years. Without any nearby galactic companions to pull it apart, the ring has been allowed to maintain its form with a kind of cosmic serenity that is almost unheard of in the universe. Yet this same isolation complicates the mystery rather than simplifying it. The most straightforward and widely accepted explanations for ring galaxies involve interactions with other galaxies. Usually, astronomers think that a ring forms when a smaller galaxy passes directly through the centre of a larger one, like a pebble dropped into a pond, sending ripples of star formation outward in a perfect circle. Sometimes, tidal interactions, where one galaxy passes near another without directly colliding, can also produce rings or arcs, as stars and gas are tugged into new patterns. But if Hoag's object is truly so far removed from other galaxies, these explanations become far less convincing. There is no obvious partner, no nearby intruder that could have caused the ring through a direct hit or a grazing pass. Even if such an event occurred billions of years ago, the culprit would have had to vanish completely, leaving no trace behind, which is extraordinarily difficult to reconcile with the laws of galactic dynamics we understand. Galaxies tend to leave fingerprints, streams of stars, clouds of gas, or visible distortions in structure. But in Hoag's object, astronomers find almost nothing of this kind. The evidence that could point to a past collision or a gravitational encounter is simply missing. The isolation of Hoag's object also makes another problem, known as the youth paradox, even more perplexing. The stars that make up the luminous ring are relatively young in cosmic terms. Unlike the ancient core, which is composed of older, more settled stars, the ring shines with the blue light of stars that were formed fairly recently, perhaps a few 100 million years ago. In the vast timescale of the universe, that is the blink of an eye. If these stars are so young, then something must have triggered a massive burst of star formation to create the ring. But if there has been no close galactic neighbour for millions of light years, what could have caused such a symmetrical, widespread wave of starbirth? The usual suspects, collisions, tidal interactions, gravitational harassment, seem to be ruled out by Hoag's object's lonely environment. Some astronomers speculate that the very emptiness surrounding Hoag's object may itself play a subtle role in shaping the galaxy. It resides in what cosmologists sometimes call a cosmic void, a region where the density of galaxies is extremely low and matter is sparse. In these voids, intergalactic gas, the diffuse material that drifts between galaxies, can move more freely without being stripped, heated, or agitated by the frequent interactions that dominate more crowded regions. In theory, this calm environment could allow gas to accumulate around Hoag's object gradually and symmetrically, falling evenly from different directions. Over immense periods of time, such a gentle inflow might settle into a circular orbit, forming a perfect ring of new stars around the older golden core. This idea is intriguing because it provides a way to form a ring without requiring a nearby galactic collision. But while the concept is elegant, it is still largely theoretical. Current computer simulations and models of galaxy formation have not yet been able to recreate a ring like Hoag's object through this process alone. The exact mechanics of how gas could flow into a galaxy in such a perfectly symmetric way, coalesce and ignite star formation remain elusive. The remote location of Hoag's object may also explain why the galaxy has retained its pristine, almost flawless appearance. In a crowded galaxy cluster, even if a ring could form, it would almost certainly be distorted within a few 100 million years by the gravitational pull of neighbouring giants. Spiral arms could be stretched, cores could be disrupted, and rings could be warped into arcs or torn apart completely. Hoag's object, by contrast, has evolved in near-total peace, shielded from the gravitational turbulence that plagues galaxies in denser regions. This quiet upbringing may have allowed its unusual structure, the luminous ring encircling a smooth spherical core, to freeze in place, unchanged, for billions of years. This solitude also helps explain the stability of the core itself. The central sphere of older stars is remarkably smooth and undisturbed. It contains little dust, shows no signs of new star formation, and appears untouched by the cosmic weather that affects more crowded galaxies. Without any nearby companions to stir up the core, feed it with fresh gas, or trigger new activity, it has remained essentially frozen in time. In a way, the core of Hoag's object is a relic, a well-preserved fossil of an earlier era in the galaxy's life. It stands surrounded by a ring of younger stars, formed much later, through a process that astronomers still do not fully understand. The galaxy is a living demonstration of cosmic longevity, with its old heart and its young ring coexisting in a delicate, isolated harmony. But this peaceful isolation does not make the central mystery disappear. In fact, it deepens it. By removing the most common mechanisms for ring formation, the galaxy's loneliness intensifies the enigma. If there are no nearby galaxies, no recent collisions, and no evident tidal interactions, then the event that created the ring must have been unlike anything we usually observe. To borrow a simple analogy, it is as if you are watching a pond and see a perfectly circular ripple, yet there is no stone, stick, or fish nearby that could have caused it. Something extraordinary must have occurred to set the stars into their precise circular formation, something unlike the usual galactic encounters we have seen across the universe. Astronomers continue to scrutinize the surroundings of Hoag's object, in search of subtle signs of past interactions. They look for ghostly streams of stars that might trace the path of a vanished intruder, faint dwarf galaxies that could be remnants of a long-lost companion, or tenuous trails of gas that might hint at an ancient encounter. Despite decades of observation, these searches have not produced conclusive evidence. No hidden partner, no faint collision scar, and no obvious clue to the ring's origin have yet emerged. The galaxy remains solitary, stubbornly resisting every attempt to categorize its past or explain its present with familiar theories. Hoag's object, therefore, is a remarkable case in many ways. Its isolation not only preserves its structure, but also challenges our understanding of how galaxies form and evolve. In crowded galactic neighborhoods, interactions and collisions dominate, making galaxies change shape, form stars, and feed their cores almost continuously. Here, in the vast emptiness, an entire galaxy has apparently developed and maintained a structure that is both extraordinarily beautiful and scientifically confounding, with a smooth, ancient core surrounded by a ring of relatively young stars. Its remote environment offers peace, stability, and an unusual opportunity to observe a galaxy in a kind of suspended animation, yet it simultaneously removes the explanations that would normally account for its most striking feature. The solitude of Hoag's object is both a blessing and a curse for astronomers. It has allowed the galaxy to remain remarkably well preserved, providing an almost pristine example of a ring galaxy. But it also deepens the mystery because it eliminates the usual suspects for ring formation. The challenge is now to find mechanisms that can operate in extreme isolation, to explain how a galaxy in a nearly empty region of space could produce a ring so perfectly circular, populated by young stars, without leaving any obvious trace of an external trigger. Whether the answer lies in the slow, symmetric inflow of intergalactic gas, some entirely unknown process, or a long-vanished companion, Hoag's object continues to defy simple explanation. Its quiet existence reminds us that the universe can produce astonishing structures even in the loneliest, most unpopulated corners of space, and that sometimes the most beautiful cosmic patterns emerge not from chaos and collisions, but from serenity, solitude, and the patient unfolding of time over billions of years. When the Hubble Space Telescope turned its powerful, crystal-clear gaze toward Hoag's object in the year 2002, the reaction from both professional astronomers and ordinary stargazers alike was one of sheer awe. The images it sent back were unlike almost anything anyone had seen before. The galaxy's perfect glowing blue ring, wrapping around a luminous golden core, seemed almost unreal, as though a masterful artist had taken the universe itself and painted a design far beyond human imagination. People looked at these photographs and felt a mixture of wonder, curiosity, and disbelief. Yet, as mesmerizing as Hoag's object already was, the real surprise came from a smaller, much fainter ring-shaped galaxy, tucked quietly in the background of the same frame. It was subtle, almost shy, sitting there behind the grandeur of the main galaxy, but its presence would spark a wave of fascination that blended scientific inquiry with the whimsical imagination of the public. This unexpected secondary galaxy was immediately nicknamed Hoag's twin, or sometimes the smaller Hoag. The choice of names reflected both its apparent similarity to the main galaxy and the sense of cosmic family resemblance that it seemed to evoke. At first glance, it appears as if the universe was showing off, presenting two identical structures at two different scales, perfectly aligned along our line of sight. It is almost as if the cosmos were echoing itself, repeating its patterns with a meticulous sense of symmetry and style. But the truth, as astronomers quickly realized, was even more extraordinary. This smaller twin is not physically connected to Hoag's object in any way. The two galaxies are separated by vast stretches of space, so distant from each other that they will never interact, collide, or influence one another in any meaningful way. Their apparent similarity is purely a matter of perspective, a cosmic coincidence so improbable that it stretches the imagination. The smaller Hoag is seen through the empty gap that lies between Hoag's object's dense golden core and its striking outer blue ring. This positioning is almost theatrical. The twin seems perfectly framed, as if the universe had deliberately placed it there to be admired, like a smaller painting hung precisely within the border of a larger masterpiece. Were it shifted by even a tiny fraction of an angle, just a few arc seconds, it might have slipped unnoticed into the background, lost among the countless faint smudges of light that populate the heavens. Yet here it is, perfectly positioned, a faint echo of the larger, more famous galaxy, peeking delicately through a gap of empty space. Studying the background twin is no easy task. Even with the incredible clarity of Hubble's optics, it remains a faint blur, just barely distinct enough to suggest a ring-like shape. Its distance makes it extremely difficult to probe in detail, and spectroscopic measurements, which allow astronomers to analyze the light from celestial objects to determine their composition, movement, and other properties, are especially challenging. Early observations suggest that the twin might itself be a ring galaxy, much like Hoag's object, but the evidence is far from conclusive. Some scientists propose alternative explanations. Perhaps it is not truly a ring galaxy at all. It could be an ordinary galaxy whose central region is obscured by a patch of dust or gas, creating the illusion of a ring from our point of view. Yet the distribution of brightness across the smaller galaxy seems to support the idea that its outer ring is genuine, hinting at a remarkable cosmic parallel. If the smaller Hoag is indeed a true ring galaxy, then we are witnessing a rare alignment of two extremely unusual objects, arranged purely by chance in the same line of sight. From a mathematical perspective, the odds are mind-boggling. Ring galaxies are themselves rare. They represent only a tiny fraction of all galaxies in the observable universe. For one ring galaxy to appear directly in front of another, and for that alignment to be visible from our vantage point on Earth is almost statistically impossible. To offer an analogy, imagine tossing a coin into the air and having it land upright on its edge twice, on opposite sides of a table simultaneously. That is the kind of improbability astronomers are grappling with when they study this double ring phenomenon. The striking alignment of Hoag's object and its distant twin has inspired two very different but equally fascinating responses: rigorous scientific curiosity and playful, almost poetic speculation. Scientists focus on questions of classification, structure, and the mechanics that might explain the visual arrangement, while the public often allows their imagination to wander. For many, the image suggests hidden patterns in the universe, a cosmic order lurking beneath what seems random, as if galaxies are part of a greater, subtle design. Some enthusiasts speculate that if we could look deeply enough and with enough precision, we might discover that these striking patterns, rare as they appear, might be more common than previously thought, simply hidden from view by the vastness of space. For professional astronomers, the smaller Hoag offers a humbling reminder of how much chance influences our observations. Had it been located even slightly off-center, Hubble's photograph would still have captured Hoag's object in all its luminous glory, but the resulting frame would not have achieved the same iconic status. Instead, the universe has allowed a rare and almost theatrical alignment, producing an image where improbability became reality. In this frame, we see not just a galaxy, but a visual metaphor for the layers of complexity and hidden structures that lie within the cosmos. We are reminded that our view of the universe is often partial, constrained by both perspective and chance, yet occasionally rewarded with extraordinary serendipity. There is another layer of scientific value hidden in the presence of Hoag's twin. Because it lies so far behind Hoag's object, the light we observe from it has already travelled past the nearer galaxy before reaching Earth. This light has passed through the gas, dust, and possibly even the dark matter halo that surrounds Hoag's object. In principle, studying this light could give astronomers indirect information about the composition, structure, and properties of the intervening material, a kind of natural cosmic backlighting that offers insights we could not otherwise obtain. Observing such a configuration is like using a flashlight shining through layers of fog to understand the density and structure of the mist. We cannot manipulate it. We can only analyze what the universe has arranged for us. So far, despite interest and repeated observations, the smaller Hoag has not yielded a wealth of additional detail. Its faintness demands long exposures and extensive telescope time, resources that are always in high demand. Consequently, much about it remains a mystery. Nonetheless, its very presence contributes to the extraordinary nature of Hoag's object. Not only is Hoag's object a rare and remarkably orderly galaxy in its own right, with its luminous core and perfect outer ring, but it also shares its most famous photograph with a distant, possibly unrelated twin. The combined image captures two rare cosmic wonders in a single frame, one nearby and prominent, the other faint and billions of light years further away. The story of Hoag's twin also highlights the broader beauty and unpredictability of the universe. In a cosmos filled with countless galaxies, stars, and nebulas, most alignments are random and fleeting. Most rare objects remain hidden, scattered across unimaginable distances, their secrets only glimpsed when the conditions are just right. Yet every so often, the universe offers a gift, a moment where rare phenomena line up perfectly, where the improbable becomes visible, and where the cosmos seems to wink at us, revealing a glimpse of its hidden symmetry and unexpected artistry. Even without detailed measurements, the smaller Hoag challenges our understanding of galaxy formation and alignment. If it is indeed a ring galaxy, then astronomers must consider what it means to have two such structures in nearly perfect alignment. Are there unknown patterns or processes that might make certain configurations more likely than current models suggest? Or is it simply an extraordinary cosmic coincidence, a reminder of the random elegance of space? These questions, while still unanswered, drive research and encourage the development of new observational strategies, hoping to catch similar occurrences and to expand our understanding of how galaxies and the universe itself arrange themselves across time and space. Moreover, the striking visual of Hoag's twin reminds us of the power of perspective. From Earth, these two galaxies appear aligned, echoing each other in a way that seems deliberate. Yet in three-dimensional space, They are separated by billions of light years, forever independent, never interacting. This duality between appearance and reality is a recurring theme in astronomy, highlighting the limitations of our perception and the importance of careful measurement and interpretation. We often rely on light, travelling vast distances across the cosmos, to reconstruct the positions, structures, and behaviours of objects far beyond our reach. Hoag's twin exemplifies the complexity of this task. A faint ring in the background becomes both a scientific puzzle and a symbol of the universe's layered depth. The fascination with Hoag's object and its twin extends beyond scientific circles. Images of these galaxies have become popular in public media, inspiring awe, wonder, and curiosity. They evoke questions about the nature of chance and order, about the subtle patterns that might underlie the apparent chaos of the cosmos. They remind us that while science seeks explanations, observation often precedes understanding, offering glimpses of extraordinary phenomena before we can fully comprehend them. For many, the combined image of Hoag's object and its background twin becomes more than data. It becomes art, a visual meditation on the beauty, rarity, and mystery of the universe. In summary, the discovery of Hoag's twin within the frame of Hoag's object represents an astonishing confluence of rarity, chance, and cosmic elegance. The smaller, faint ring is neither part of the main galaxy nor likely to ever interact with it, yet its alignment transforms the image into something iconic. Its presence highlights the challenges of astronomical observation, from the difficulty of studying extremely distant objects to the role of chance in the phenomena we happen to see. It also serves as a poetic reminder that the universe often reveals layers of complexity and hidden beauty, just waiting for the right moment and the right perspective to be observed. Hoag's twin, faint though it may be, contributes an enduring sense of wonder, demonstrating how even in the cold, vast reaches of space, chance and coincidence can create scenes of extraordinary elegance that captivate both the mind and the imagination. In the end, Hoag's object and its distant twin invite us to consider not only the mechanics of galaxies and light, but also the extraordinary improbabilities that make the universe a place of endless fascination. Through the Hubble Space Telescope, we are given a glimpse of what the universe can arrange when chance, perspective, and distance align perfectly. We see not just a galaxy, but a cosmic story in layers, a brilliant golden core, a radiant blue ring, and a faint twin in the distance, separated by billions of years and yet perfectly framed in a single photograph. This rare visual alignment exemplifies the delicate balance of chaos and order that characterizes the cosmos, offering scientists and the public alike a moment to marvel, to question, and to imagine the many unseen layers of the universe that remain waiting for discovery. Even as research continues and technology advances, Hoag's twin remains a symbol of the unknown. Its faint light, travelling across the expanse of time and space, carries with it the possibility of new discoveries, whether through detailed study or serendipitous observation. The galaxy may be just a small smudge of light in the background, but it is also a cosmic beacon, a reminder that even in the emptiest stretches of the universe, the improbable can appear, framed in perfect symmetry and captured forever in a single unforgettable image. For astronomers, it is an object of study, a puzzle to unravel, and a tool for learning about the intervening material in Hoag's object. For everyone else, it is a moment of pure wonder, a visual testament to the universe's ability to surprise, inspire, and astonish in ways that are both scientific and profoundly poetic. Thus, the double vision of Hoag's object and its distant twin remains one of the most captivating images in modern astronomy. It is a reminder that while much of the universe is vast, dark, and empty, occasionally it arranges its elements in ways so improbable and so beautiful that we cannot help but pause, gaze, and marvel at the patterns hidden within the endless cosmos. In this single frame, we see a luminous galaxy, its golden heart encircled by a pristine blue ring, and behind it, a faint echo from billions of light years away. Two galaxies, aligned by chance, captured by the most powerful telescope ever built, offering a window into both the mechanics and the poetry of the universe, and leaving us to wonder what other cosmic coincidences await discovery among the stars. The ages of the stars in Hoag's object, a galaxy so strange and captivating, are among the most fascinating clues to its mysterious past. Yet, instead of offering straightforward answers, these ages seem to deepen the puzzle, leaving astronomers scratching their heads. To truly understand the enigma, we need to look closely at the two main components of this galaxy: the bright golden core and the dazzling blue ring that surrounds it. These two regions not only differ in colour and shape, but they also tell entirely different stories about the passage of time in this extraordinary celestial structure. At the very centre of Hoag's object lies the golden core. This core is a dense sphere of stars that shine with a warm yellow light, the kind of gentle glow produced by stars that have matured, stars that have spent billions of years fusing hydrogen into helium, quietly burning in the stable phase of their lifetimes. Astronomers estimate that most of these stars are several billion years old, making them some of the oldest visible members of the galaxy. This part of the galaxy makes a certain kind of sense. In most galaxies, the central bulge, the heart of the structure, tends to be home to older stars. Often, these central regions have an elliptical shape, with stars packed together densely, moving in random orbits and shining steadily with a warm golden light. The core of Hoag's object follows this expected pattern, presenting a familiar scene in an otherwise extraordinarily unfamiliar galaxy. But everything changes once we move outward toward the ring. This is where the real puzzle begins. The ring is not golden, but a brilliant, almost electric blue. This blue hue is the hallmark of youth in the cosmos. Stars that shine with such intense blue light are massive, hot, and extremely energetic. They burn their nuclear fuel quickly, living fast and dying young, often in a few tens of millions of years, mere infants compared to the multi-billion-year age of the stars in the core. Some of the stars in the ring may be only a few million years old, barely a blink in cosmic time. The contrast between the ancient core and this youthful ring is stark, almost jarring, like discovering a city where an ancient cathedral is suddenly surrounded by ultra-modern skyscrapers with no transitional eras in between. What makes this contrast even more striking is the vast empty space between the core and the ring. There is a gap, tens of thousands of light years across, that seems almost completely devoid of stars. It is a dark, silent void that acts as a clear dividing line between the old, quiet heart of the galaxy and the vibrant young halo that encircles it. This gap accentuates the sense that Hoag's object contains not one, but two entirely separate histories, each frozen in time yet living side by side. In more typical galaxies, the age of stars changes gradually from the centre to the outer regions. You might start with ancient stars in the central bulge, then find progressively younger stars as you move outward, forming a smooth gradient. But Hoag's object defies this norm. Its age distribution is sharply divided, almost like two distinct timelines superimposed onto a single galactic canvas. Astronomers have gone beyond simply observing colours to try to pin down the ages of these stars more precisely. Using a technique called spectroscopy, they can split the light from the ring into its component wavelengths. This allows them to see the fingerprints of different chemical elements, which in turn reveals the age and composition of the stars. What they find confirms the striking visual impression. Many stars in the ring are extremely young, less than 10 million years old, while others have ages of several 100 million years. This tells us something important. The ring has not been formed in a single dramatic event, but has been steadily creating stars over a long period. Star formation is still active in the ring today, in contrast to the ancient core, where star formation stopped billions of years ago. This contrast raises a fundamental question. If the core is so old and dormant, where is the fuel for the ring's ongoing star formation coming from? Young stars require dense clouds of cold gas to form, clouds that collapse under gravity to ignite new stars. Somehow, Hoag's object must have accumulated or retained a supply of gas specifically in the ring, despite the absence of nearby galaxies that might donate material and the lack of evidence for a recent galactic collision. The source of this gas remains a profound mystery. Several theories have been proposed to explain how the ring could continue to form stars. One idea is that the galaxy has been slowly accreting gas from the intergalactic medium, the sparse and diffuse mixture of hydrogen and other elements that exist in the vast spaces between galaxies. In this scenario, streams of pristine hydrogen could have gradually fallen into the gravitational well of Hoag's object over hundreds of millions of years. Once captured, this gas would settle into stable orbits, forming the circular structure we see today and begin condensing into new stars. While this might explain why the ring continues to harbour young stars, it does not fully account for the remarkable precision of its circular shape. Accreting gas typically arrives in a messy, chaotic fashion, producing warped disks or irregular structures rather than a nearly perfect ring. Another possible explanation involves past interactions with other galaxies, perhaps ones that were small and rich in gas. If such a dwarf galaxy had come close to Hoag's object, gravitational forces could have stripped gas from the smaller galaxy and helped it settle into the ring. This scenario could explain why the ring contained such young stars while leaving the old core largely untouched. However, the challenge is that astronomers see no clear remnants of such an encounter, no tidal tails or leftover debris that would normally persist for hundreds of millions of years. The evidence, if it exists, has either disappeared or is hidden beyond our observational reach. The age paradox of Hoag's object also forces astronomers to reconsider the timescales involved in star formation. If the ring formed rapidly in a single burst, as sometimes happens after galactic collisions, the stars within it should be nearly identical in age, with only slight variations. But in Hoag's object, the data show a wide range of ages in the ring. Some stars are mere infants of a few million years, while others have been burning for several 100 million years. This indicates that star formation has been a sustained process, taking place over a significant fraction of cosmic time rather than in a single dramatic moment. Whatever event or process gave rise to the ring did not merely trigger a one-time burst, it set up conditions for ongoing star formation that continue even today. The chemical composition of the ring's stars provides another intriguing clue. While the differences are subtle, they are telling. Stars in the ring tend to have slightly lower amounts of heavy elements, those elements beyond hydrogen and helium, than the stars in the core. This suggests that the gas from which the ring formed had a different evolutionary history, less enriched by previous generations of stars. In other words, the ring's material did not originate from the core or from leftover remnants of earlier star formation. Instead, it seems to have come from a distinct reservoir of gas, possibly the intergalactic medium or a disrupted dwarf galaxy, reinforcing the idea that the core and ring represent two separate galactic histories brought together in one extraordinary object. The more astronomers study Hoag's object, the more it appears that this galaxy is a combination of two independent worlds. Its heart is old, inactive, and settled into a state of quiet stability. Its outer ring is young, active, and continuously forming new stars. These two regions exist side by side, yet they evolve on entirely different timescales, with no obvious mechanism connecting them. It is as if someone took a castle built in the Middle Ages and placed it exactly in the centre of a bustling modern city, yet removed every sign of what came before or what might have followed. There is no bridge, no gradual transition, just two extremes juxtaposed in a single frame, forcing us to rethink our assumptions about how galaxies grow and evolve. One of the most confounding aspects of the age paradox is how neatly the division is maintained. Across tens of thousands of light years, there is no significant population of intermediate age stars filling the gap between the ancient core and the young ring. This absence is remarkable. In most galaxies, star formation is messy and continuous, producing a spectrum of stellar ages that blend seamlessly from centre to edge. But Hoag's object shows an almost surgical separation. It is as if two distinct timelines, one billions of years old and the other barely a few million years, were squashed together, occupying the same space but refusing to intermingle. Even the dynamics of the stars contribute to the mystery. The stars in the core move in random elliptical orbits, consistent with a long history of gravitational interactions that have allowed the system to settle into equilibrium over billions of years. In contrast, the stars in the ring travel in more orderly, nearly circular paths. This kinematic difference mirrors the age and compositional differences, suggesting that the two regions did not simply form together, but were influenced by separate processes. Whatever shaped the ring must have preserved its delicate circular symmetry, while leaving the core largely undisturbed, a challenge that many standard galactic formation scenarios struggle to explain. The puzzle of Hoag's object becomes even deeper when we consider the implications for galaxy evolution in general. If a galaxy can contain two such radically different stellar populations, each with its own history, it forces astronomers to expand their ideas about how galaxies acquire gas, form stars, and interact with their environments. The galaxy challenges the assumption that star formation follows a smooth gradient from old centers to young outskirts. It suggests instead that under certain conditions, galaxies can preserve distinct episodes of star formation, creating sharply divided populations that coexist for billions of years. Moreover, the continued presence of star formation in the ring raises practical questions about the longevity of gas reservoirs. Star formation consumes gas, so for the ring to remain active over hundreds of millions of years, it must either have had an exceptionally large initial supply or must continue to receive fresh material. The intergalactic medium could provide this, but capturing it in a way that produces a near-perfect ring is difficult. Interactions with dwarf galaxies are also possible, but the lack of clear evidence leaves this idea speculative. In either case, the ring's existence implies a delicate balance of gravitational forces, gas dynamics, and star formation efficiency, maintained over extraordinary lengths of time. Perhaps the most poetic aspect of the age paradox is its storytelling power. Hoag's object reads like a cosmic narrative, a tale of two epochs, two processes, and two destinies intertwined in one galaxy. The golden core whispers of ancient history, of stars that have burned steadily for billions of years and now shine in tranquil harmony. The blue ring sings of youth and vigour, of matter still collapsing under gravity to ignite new generations of stars, a living, evolving tapestry in contrast to the frozen serenity at the centre. Together, these two regions tell a story that is both unified and divided, beautiful and bewildering, familiar and utterly alien. At first glance, it may seem like a small observation, almost trivial. Yet for astronomers, this simple fact is extraordinary, because it highlights just how different Hoag's object is from the billions of other galaxies that populate the universe. When we look at galaxies, we often imagine swirling, majestic forms or enormous, smooth ellipses that seem calm and eternal. There are countless galaxies in the cosmos, yet they tend to follow a small number of patterns, a set of familiar shapes and behaviours that can help scientists classify and understand them. Spirals, for instance, are some of the most common and most easily recognised galaxies. These galaxies feature long, sweeping arms that wind gracefully around a bright, glowing central core. The arms are not just beautiful, they are regions where countless stars are being born. The twisting patterns are the result of subtle, invisible forces known as density waves, areas of slightly higher gravity that move through the disk of the galaxy. These waves compress gas and dust as they sweep along, triggering the formation of new stars and giving the arms their characteristic structure. Within the broad category of spirals, there is another familiar subclass known as barred spirals. These galaxies are distinguished by a straight, elongated feature, a bar running across the central core. This stellar bar is far more than decoration. It acts almost like a cosmic conveyor belt, guiding streams of gas and stars toward the centre, helping the galaxy grow, evolve, and even shape its spiral arms. Elliptical galaxies, in contrast, are simpler in appearance. They tend to be smooth, round, or oval in shape, and dominated by older, redder stars. There are no spiral arms to stir up the imagination, no twisting bars to complicate the picture. Yet even these galaxies have internal patterns and distributions that tell a story of formation and evolution over billions of years. Even when galaxies look irregular, messy, or chaotic, astronomers can usually detect a hidden order, a subtle way in which stars and gas have been arranged over cosmic time. Hoag's object, however, refuses to fit neatly into any of these categories. It stands apart, a galaxy that does not conform to the patterns astronomers rely on to organise the universe. Its difference is most immediately noticeable in what it lacks. The galaxy has no twisting spiral arms. It does not have the characteristic arcs of stars that reach outward from the centre, curling and bending as if caught in some invisible cosmic whirlpool. Spiral galaxies dominate the local universe, the region of space relatively close to our own Milky Way, and their arms are the primary sites of ongoing star formation. Yet in Hoag's object, these twisting arms are entirely absent. The galaxy's most striking feature, the outer ring, is not an arm that has looped back around on itself. It is a separate circle, perfectly round, with no visible connection to the central core through a spiral pattern. The ring floats at a distance, like a halo suspended in space, and this very separation is part of what makes Hoag's object so puzzling. There is also no central bar. Barred spirals, as mentioned, feature a line of stars stretching through the core, a structure that naturally forms as the galaxy evolves. Bars are not fleeting. They appear in both young and older galaxies, suggesting that they are a common and almost inevitable feature in galactic development. In Hoag's object, however, no bar is visible. Without it, the familiar mechanisms that shape and feed spiral galaxies, the dynamic movements of gas and stars along the bar, the compression and channeling that produce arms, are absent. The galaxy's core instead resembles that of an elliptical galaxy. Smooth, round, and devoid of the dust lanes, clouds of gas, or clumps of young stars that we expect to find in spiral galaxies. The centre is serene, almost sterile, yet profoundly beautiful, its golden stars glowing evenly without the scars of collisions or turbulent events. Even more striking is the lack of disorder. Most galaxies, even those that appear symmetrical and orderly from a distance, reveal imperfections when observed closely. Spiral arms often vary in brightness from one side to the other. Dust lanes may cut unevenly across the central bulge, and faint tidal streams, the ghostly remains of past galactic encounters, stretch outward into space. These irregularities are the fingerprints of a galaxy's history, subtle records of encounters, mergers, or uneven distributions of gas and dark matter. Hoag's object shows none of these signs. Its ring shines uniformly around the galaxy, a flawless circle of blue young stars. The core is perfectly symmetrical, and the space between the ring and the centre is completely empty, a dark void separating the two. It is as though every chaotic element that usually accompanies galactic evolution has been filtered out, leaving only two pristine structures, the smooth central core and the magnificent outer ring. This structural simplicity is remarkable and baffling. Galaxies rarely remain clean or perfectly symmetrical for long. Even in the quietest regions of space, interactions with neighbouring galaxies, minor mergers, and the uneven spread of gas and dark matter tend to create lopsidedness over time. In theory, Hoag's object should display some evidence of these processes, some faint scars marking its history. Yet under the sharp gaze of the Hubble Space Telescope, none of these features are visible. No tidal streams, no warped rings, no off-centre star clusters. The galaxy appears almost untouched, a perfect cosmic gem suspended in isolation. Some astronomers have suggested that the absence of spiral arms and a central bar might be due to the galaxy's unusual mass distribution. If Hoag's object possesses an exceptionally stable gravitational potential, possibly influenced by an unusually smooth and evenly distributed halo of dark matter, it might prevent the formation of density waves, the invisible ripples in a galaxy's disk that ordinarily produce spiral arms. This theory may account for the lack of twisting arms, but it still leaves questions unanswered. It does not explain why the outer ring is so remarkably uniform, nor why the inner region remains empty and undisturbed. It is one thing to prevent arms from forming, but it is quite another to maintain a perfectly circular ring without allowing gas or stars to drift inward or create clumps along the way. Explaining the absence of a bar is even more challenging. In disk galaxies, stars naturally respond to variations in the gravitational field, and bars almost inevitably emerge as a result of this process. They are common, appearing in both newly formed and mature galaxies, and are thought to be a natural stage in galactic evolution. If Hoag's object ever had a bar, it would have left behind traces, perhaps a central bulge, a faint inner ring, or a distorted distribution of stars. Yet none of these remnants are present. It is as if the galaxy bypassed this stage entirely, avoiding one of the fundamental evolutionary steps that shape most disk galaxies. Another unusual feature of Hoag's object is the absence of dust. Spiral galaxies are threaded with dark, winding lanes of dust that trace the structure of the arms and provide the raw material for star formation. Dust acts as both marker and fuel, revealing the pathways along which new stars emerge and helping to sustain the ongoing life of the galaxy. In Hoag's object, however, the central core is completely free of dust. Even the ring shows no dark patches or clouds that would indicate the presence of dust. This cleanliness not only contributes to the galaxy's pristine appearance, but also hints at the unusual conditions under which the ring formed. The absence of dust suggests that the formation of the ring did not involve the violent, gas-rich processes that are typical in the spiral galaxies we know and love. Instead, the ring seems to have formed under calmer, more ordered conditions, as if the galaxy itself enforced a kind of cosmic discipline on the creation of new stars. When all of these absences are considered together, Hoag's object emerges as something of a structural ghost. It is a galaxy that has shed nearly every feature that astronomers usually rely on to classify and understand galactic forms. There are no arms, no bar, no dust lanes, no tidal scars, no asymmetries. All that remains is the golden core and the improbably perfect ring that surrounds it. It stands alone, resisting the neat categories of spiral, elliptical, or irregular. Its very existence challenges astronomers to rethink the rules they apply to galaxy formation and evolution. It is tempting to imagine Hoag's object as a finished, settled galaxy, one that has reached a stable state and will remain unchanged for billions of years. The smoothness of its core, the flawless ring, and the lack of chaotic features all suggest a galaxy that has completed its journey. Yet the active star formation in the ring tells a different story. The outer circle is not a relic of the past. It is a vibrant, living structure, full of young, blue stars being born in real time. This indicates that the galaxy is still evolving, though in a manner that does not fit standard models or familiar blueprints. It is growing and changing quietly, without the dramatic gestures of spirals or barred galaxies. Whatever forces shaped Hoag's object did so with an almost magical subtlety, leaving no fingerprints of the processes that typically dominate galactic evolution. No collisions, no mergers, no bar formation, no twisting arms, no dust storms. None of the usual cosmic dramas are evident. Instead, we see a galaxy that has found an extraordinary balance, a form that is stable, yet still capable of creating new stars, a galaxy that defies the conventional narrative of growth and change. It is as if the universe itself has sculpted a masterpiece in isolation, revealing the remarkable possibilities of order and symmetry in a cosmos usually dominated by chaos and turbulence. The outer ring, shining with the light of freshly formed stars, seems almost suspended in space, orbiting the golden core with a precision that appears deliberate, intentional, almost uncanny. Its perfect circularity contrasts sharply with the irregular and often messy shapes of other galaxies. The ring is more than a visual spectacle. It is a clue, a piece of a puzzle that challenges every assumption about how galaxies come into being. The core, in turn, glows with a warm, mature light, hinting at an ancient past, a history that remains hidden because the usual signs of disruption are absent. The void between the core and the ring emphasizes the galaxy's unusual structure, creating a sense of separation and mystery that sets Hoag's object apart from every other galaxy in the nearby universe. Even the galaxy's surroundings provide context for its strangeness. Most galaxies exist in clusters, interacting with neighbors, pulled and prodded by gravitational forces, occasionally colliding or merging in spectacular cosmic dances. Hoag's object, by contrast, seems remarkably isolated, living in relative solitude. This isolation may contribute to its pristine appearance, preventing external forces from introducing irregularities or distortions. Yet even isolation cannot fully explain the galaxy's unique features. Other galaxies in similarly quiet regions often show some form of asymmetry or bar structure. But Hoag's object remains a perfect circle around a flawless core, a serene island in a turbulent cosmic ocean. Scientists continue to debate the processes that could produce such a galaxy. Could it be that Hoag's object represents a rare stage of galactic evolution, one that almost never occurs? Might it be the product of conditions so unusual, perhaps a precisely balanced dark matter halo, an unusually smooth distribution of mass, or an exceptionally calm formation history, that only a handful of such galaxies exist in the observable universe? These questions remain unanswered, as does the deeper mystery of how the outer ring formed with such regularity while the core remained untouched. In the end, Hoag's object is a reminder of the universe's capacity to surprise, to defy expectations, and to create forms that challenge our understanding. It is a galaxy that resists categorization, that cannot be neatly placed within the frameworks astronomers have developed over centuries of observation. Its very existence demands a reconsideration of the rules that govern galactic structure, of the processes that lead to star formation, and of the role of symmetry and order in a universe often thought to be dominated by chaos. The galaxy's smooth core, perfect ring, and absence of dust, bars, and spiral arms make it a ghostly yet luminous presence, a celestial enigma that continues to captivate astronomers and enthusiasts alike. No matter how much we study Hoag's object, it continues to hold secrets. The more we observe it, the more questions arise. How can such a stable configuration exist in a universe where chaos is the norm? How did the ring form without triggering disorder in the core? Why does the galaxy show no evidence of past interactions, mergers, or bar formation? These mysteries ensure that Hoag's object will remain a topic of fascination, a challenge to our understanding of galactic evolution, and a testament to the richness and complexity of the cosmos. It is, in essence, a galaxy unlike any other, a structural ghost that carries the dual nature of calm and activity, stability and growth, simplicity and complexity. It is a rare cosmic jewel, shining with both the wisdom of the old stars in its heart and the youthful energy of the new stars forming along its ring. Hoag's object reminds us that even in a universe governed by known physical laws, exceptions exist, and these exceptions often teach us the most about the underlying rules. They show us the limits of our knowledge, the surprises still hidden in the depths of space, and the remarkable beauty that can emerge when order prevails in a place where chaos is expected. By observing Hoag's object, astronomers are not merely cataloguing a strange galaxy, they are peering into a cosmic laboratory, a rare case that tests theories of formation, stability, and evolution. It challenges the assumptions about what is typical or inevitable, revealing that galaxies can, under the right conditions, achieve forms of symmetry and elegance that seem almost impossible. And yet, despite its perfection, the galaxy is alive. When astronomers first looked at pictures of Hoag's object, one thing stood out more than anything else: the incredible roundness of the ring. It was not lopsided, it was not stretched, it was not bent out of shape in any direction. The ring appeared almost perfectly circular, the same width all the way around, and no matter how you turned the image in your mind, it was always at the same distance from its glowing golden core. In the vast universe, where chance and chaos shape most things, that kind of accuracy is a rare treasure. In fact, such neatness almost never happens in astronomy. Galaxies are usually wild, uneven, and unpredictable. Nature seldom creates anything that is perfectly round on such a gigantic scale. When you look at galaxies with rings, most of them reveal flaws upon closer inspection. Some parts of the ring are thicker, some brighter, some blurrier than others. This unevenness often comes from the way stars are born at different rates, or from leftover debris scattered after a galactic collision. Even the most beautiful ring galaxies usually suffer from distortions. Over time, the gravitational pull from nearby galaxies, or even the uneven tug of their own inner mass, tends to twist those rings into shapes that are more like stretched ovals than perfect circles. Yet Hoag's object seems immune to all of that. Its ring does not sag or stretch. It looks as though some master craftsman used a compass to draw it onto the universe itself. Its symmetry is so sharp and clear that astronomers often use it as a testing ground. When they design new image processing software, they sometimes point it at Hoag's object. If the program can trace the ring as a perfect circle without error, then they know their code is working well. The ring of this galaxy is that clean, that precise, that dependable. But herein lies the problem. The universe is not supposed to work that way. Perfection is suspicious. Galaxies are not frozen paintings, they are living systems. Stars are always moving. Gas clouds drift and swirl. Gravity tugs and pulls in countless ways. External forces from neighbouring galaxies also interfere, bending and twisting structures over millions upon millions of years. Even if Hoag's object lived all alone in the quiet darkness of space, without another galaxy close enough to disturb it, its own inner gravitational balance should slowly warp the ring. No galaxy is perfectly smooth on the inside. Mass tends to clump, to gather, to shift around, and those clumps usually disrupt circles, stretching them until they no longer look pure. Yet this galaxy seems locked in a timeless moment. Its ring remains as round as though no time had passed at all, as if frozen in cosmic perfection. To achieve that balance, the mass of the galaxy must be arranged with almost miraculous precision. Every particle, every hidden lump of matter would have to be distributed so evenly that it creates a steady pull in every single direction. Such a thing is not impossible, but it is rare beyond belief. One explanation offered by scientists is that Hoag's object might be wrapped in a particularly smooth and spherical halo of dark matter. Dark matter, though invisible to our eyes and undetectable by ordinary telescopes, exerts gravity. If this hidden halo were unusually well shaped, like a flawless bubble surrounding the galaxy, it could tug on the stars in the ring equally from all sides. That would allow the stars to orbit the center in circles so perfect that the ring appears motionless and pure even after hundreds of millions of years. The difficulty is that mapping dark matter is one of the hardest challenges in modern astronomy. We cannot see it, and we can only guess its shape by watching how visible stars and gas move. No study so far has been able to confirm that Hoag's object actually has such a smooth spherical dark matter halo. The idea fits, but it remains only a possibility. Another thought is that perhaps the ring was born in a sudden event, a collision or an impact that happened at just the right angle, leaving behind a perfect circular shockwave of stars. If such an event occurred recently, the ring might not have had enough time to distort, but this suggestion does not hold up under deeper examination. For one, astronomers know that stars have been forming in the ring for hundreds of millions of years. That is far too long for a fragile temporary structure to stay so neat. A quick, violent event should have left behind a lopsided or ragged circle, something that slowly unraveled into chaos. But what we see in Hoag's object is not temporary nor fragile. It is steady, glowing, and active. Some scientists put forward another possibility. Maybe the uniformity of the ring is not caused by what formed it, but by the way the stars inside it are moving now. If every single star in the ring orbits in the same plane, and if their orbits are nearly flawless circles instead of ellipses, then to us, looking from Earth, the ring would appear as a perfect circle. But that idea only replaces one question with another. How did so many stars end up moving in such precise unison? Galaxies are usually messy gatherings of stars, each one with its own direction, its own eccentric orbit, its own little chaos. For so many stars to behave in such a disciplined way is like looking at a swarm of bees flying in formation, each one perfectly aligned without bumping into the others. Nature does not usually choreograph things so smoothly. Then there is the issue of the empty gap. Between the bright blue ring and the golden core lies a wide space that looks strangely bare. In most galaxies, even those with rings, there is usually some spillover, stray stars or clouds of gas that drift into the middle region, filling the space between core and ring. In Hoag's object, the gap is sharp and clean, as if someone swept it free of debris. The ring hangs at a precise orbital distance with nothing allowed to intrude. This sharp separation not only makes the galaxy look more beautiful, but also deepens the mystery of how such a neat arrangement could exist. Time, too, becomes part of the puzzle. Structures in the universe rarely remain stable for billions of years. Even the smallest nudges from gravity, the faintest push from drifting gas, or the gradual migration of stars usually change the shape of galaxies over the ages. If Hoag's object has looked this perfect for most of its lifetime, then some hidden mechanism must be working constantly to preserve that balance. But what could it be? Is it the pull of dark matter, guiding the stars like an unseen hand? Is it some special arrangement of orbital resonances, where the timing of the stars' movements locks them in place? Or is there some unknown force that we have not yet discovered, a rule of nature that only reveals itself in galaxies like this one? This desire for perfection is the very reason why Hoag's object has captured so much attention. Every time astronomers try to explain it, they run into a choice. Either they can explain how the symmetry remains so exact, but then they cannot explain the constant star formation in the ring, or they can explain how the ring is alive with activity, but then the symmetry should have been disturbed long ago. Somehow, the galaxy insists that both things are true at once. It is perfectly shaped and yet full of vibrant life. In this way, it feels as though two impossible realities overlap, and Hoag's object exists where they meet. dark matter only deepens the mystery. For decades, dark matter has been one of the most powerful tools in astrophysics. We cannot see it, but we can measure its pull. It reveals itself in the way stars and gas move, especially in the outer regions of galaxies where visible matter alone cannot explain the speeds we observe. Astronomers estimate the amount of dark matter in a galaxy by comparing its visible light to the motions of its stars. Usually the results are consistent. Galaxies need a great deal of dark matter to explain their stability. But Hoag's object refuses to fit that pattern. When scientists measure how fast the stars in the ring and the core rotate around the centre, the numbers do not match what they expect. In most galaxies, rotation curves, the graphs of speed versus distance, remain flat or even rise at large distances from the centre. This shows that dark matter is pulling strongly on the outskirts. But in Hoag's object, the stars in the ring are not moving as fast as they should be. It is as though the invisible halo of dark matter is weaker, thinner, or shaped differently than usual. One idea is that this galaxy simply has less dark matter than others. That would be shocking, because ring galaxies are thought to need strong halos of dark matter to remain stable. Without enough of it, gravity would wobble, and the ring should sag, bend, or shatter over time. Yet Hoag's object's ring looks firm, even, and enduring. Another thought is that the dark matter is present but spread out in an unusual way. Perhaps flatter, perhaps more diffuse, perhaps arranged in a geometry we have not seen before. In most galaxies, the region around them called the halo usually looks like a round bubble of invisible material that surrounds the galaxy. This halo is not made of light or gas, but of something we cannot see directly, and in many galaxies it has a very smooth and even shape. Its density becomes greater as you move closer to the centre of the galaxy, as though the halo were gently gathering everything toward the middle. But Hoag's object does not seem to follow this usual pattern. Some astronomers think its halo might not be so smooth or so perfectly round. Instead, it might be flatter or lopsided, or perhaps its edge is unusually sharp, like a cliff in space. If the edge of the halo is sharp, it could bend and twist the paths of the stars in unusual ways, which could explain why the space between the golden core in the middle and the blue ring on the outside is so strangely empty. In that middle zone, there are very few stars. If the pull of gravity in that area is unstable, then any stars or gas clouds that try to remain there would not be able to stay in one place for long. They would either fall inward toward the core or be flung outward toward the ring. That may be the reason the gap between the centre and the ring looks so clean and empty, almost like someone swept it clear. Because Hoag's object behaves so differently from other galaxies, some astronomers have even suggested that it might be an example of a galaxy where the laws of gravity work in a different way. Usually scientists explain the strange motions of stars in galaxies by saying that there must be something extra pulling on them, something called dark matter, which is invisible but thought to make up most of the matter in the universe. But there is another, more daring idea. Perhaps the problem is not that we are missing matter, but that our understanding of gravity itself is incomplete. This idea is known as modified gravity. It suggests that when accelerations are extremely weak, like at the far edges of galaxies, gravity might behave differently than what Isaac Newton or Albert Einstein described. In that case, maybe galaxies don't always need dark matter to explain their movements. This idea is very controversial, because most evidence still seems to support the existence of dark matter. Yet Hoag's object has one of those puzzling rotation profiles, the way its stars and gas clouds move around its centre, that does not match the usual rules. It is exactly the sort of strange case that makes astronomers wonder whether modified gravity should at least be tested. The puzzle grows even deeper when we remember that dark matter is not only supposed to guide the movement of stars, it also plays a role in how galaxies collect and keep the gas that creates new stars. Normally, the pull of a dark matter halo holds gas close, preventing it from escaping into the emptiness of space. This constant supply of gas allows galaxies to go on making stars for billions of years. So here is the question. If Hoag's object has a halo that is weaker, flatter, or shaped differently, how did it manage to gather and hold on to the gas that keeps feeding its bright blue ring of the young stars? Without that hidden dome of gravity, the ring might have scattered and broken apart long ago. The mystery becomes even more intriguing because Hoag's object lives in a very lonely place. Many galaxies are found in groups, clusters, or crowded neighbourhoods where they pull and tug on each other with their gravity. But Hoag's object sits all by itself in a rather empty part of the universe. This makes it a good candidate for studying the spread and shape of dark matter, because there are no nearby galaxies whose gravity could interfere with the measurements. In theory, that should make things easier for astronomers. Without neighbours disturbing it, the galaxy should reveal its dark matter structure more clearly. But even with that advantage, the results still don't fit neatly into the model scientists use for halos. Something about Hoag's object refuses to match the usual picture, and the difficulty does not stop there. The galaxy is very far away, lying at a distance of about 600 million light-years from Earth. That great distance makes the challenge even harder, because the farther away an object is, the more difficult it becomes to measure its details with precision. When astronomers try to measure the speed of stars at that distance, especially the faint ones in the outer ring, the readings are often uncertain. Instead of relying only on stars, they also track the motion of great clouds of gas, which glow and shift as they orbit. These clouds act as markers, but even they can be misleading. Winds from newly born stars or small disturbances that happened in the galaxy's past can nudge the gas and change its motion slightly. Those little changes add confusion to the measurements, making it difficult to draw a clear picture of the galaxy's dark matter halo. For now, the numbers we have are not very comforting. They do not give scientists strong confidence in one answer or another. Hoag's object remains an enigma, a galaxy whose beauty hides a deep scientific riddle. Perhaps when future telescopes, sharper and more powerful than those we have today, are launched into space, astronomers will finally be able to measure its movements more accurately. With better data, we might finally discover whether Hoag's object is wrapped in an unusual kind of dark matter halo, or if it is a place where the laws of gravity itself need to be rewritten. Until then, it continues to spin in silence, keeping its secret 600 million light-years away. When the Hubble Space Telescope pointed its powerful eye toward Hoag's object in the year 2002, it was not the first time astronomers had studied this strange and beautiful galaxy. In fact, scientists had already been fascinated by it for more than half a century. Since the moment it was first noticed, it had stood out as something unusual, something that did not quite fit into the familiar patterns of galaxies like spirals or ellipticals. But before Hubble, all the earlier pictures of Hoag's object were taken from telescopes on the ground, through the shifting blur of Earth's atmosphere. For their time, those photographs were astonishing, but they lacked the sharpness needed to reveal the galaxy's hidden secrets. What people could see looked mysterious, but the details remained buried in a haze. That situation changed instantly with Hubble's advanced cameras and its position high above the distorting blanket of Earth's air. Suddenly, the blurry galaxy that had puzzled astronomers for decades appeared in stunning clarity. The image that Hubble captured was not only sharper than anything seen before, it was so crisp, so flawless, that it quickly became one of the most iconic astronomical photographs of the early years of the 21st century. It was shown in newspapers, on television, in classrooms, and across the growing internet. Scientists admired it for the new details it revealed, and members of the public fell in love with its almost magical beauty. The picture sparked a wave of wonder that connected professional astronomy with everyday people in a way that few galaxies ever had. Before Hubble, Hoag's object had looked like a fuzzy golden dot surrounded by a faint ghostly ring. The central core seemed smeared, and the ring's edges were softened until they blended into the background of space. One could make out the basic structure, but the finer points, the precise spacing of the stars in the ring, the empty gulf of blackness between the core and the ring, the smoothness of the golden sphere at the centre, were hidden in the blur. Hubble changed all of that. With its advanced optics and its home above the atmosphere, the telescope delivered an image that brought those details into perfect focus for the very first time. The ring was no longer just a vague band of light. It was revealed as a structure made up of thousands upon thousands of bright, hot, youthful stars, glowing blue with the intensity of cosmic fire. They were crowded into a narrow circular zone, their combined radiance outlining the ring like a neon halo floating in the depths of space. The ring's width remained astonishingly consistent all the way around. The star clusters inside it were spread out evenly. There was no clumping, no scattering, and no disruptions that might have hinted at a violent past. The core, too, was transformed by Hubble's gaze. Instead of a messy bulge of light, it appeared smooth, flawless, and golden. Its glow came from older stars that had burned steadily for billions of years, stars cooler and more mature than the hot blue ones in the outer ring. There were no streaks of dust slicing across it, no knots of new stars being born, and no irregular features that might have pointed to recent collisions or turbulence. It was a perfect golden sphere floating at the heart of a perfect blue ring. The sheer smoothness of the core made the Hubble picture almost unbelievable. It looked less like a natural galaxy and more like something designed with careful intention, a cosmic work of art. And then came the surprise that made the image unforgettable. Nestled in the background, perfectly aligned in the empty space between the golden core and the glowing blue ring, there appeared a second galaxy. It was faint, small, and very far away, but it too had a ring shape, almost like a miniature version of Hoag's object itself. The alignment was so precise that it seemed like a cosmic joke, as though nature had decided to create a double ring illusion just for us to marvel at. Astronomers pointed out how staggeringly unlikely it was for two ring-shaped galaxies to line up in this way by chance. This one detail, more than anything else, made the photograph go viral across the world. But the image was not just beautiful, it also carried valuable scientific information. By studying the colours of the stars in the core and in the ring, astronomers could estimate their ages. The soft yellow tones in the centre revealed that it was made of older, cooler stars, while the intense blue glow of the ring showed that it was filled with young, massive stars that would live only a few million years before burning out. This striking difference in age and colour made the galaxy even more mysterious. How could two such different structures, the ancient golden core and the youthful blue ring, exist together in such flawless harmony? The symmetry of the ring also gave astronomers a chance to test their theories about how the galaxy might have formed. One common idea was that the ring had been created by a cosmic collision, perhaps when a smaller galaxy slammed through the centre of another. But if that had happened, scientists would expect to see signs of violence, distorted shapes, uneven clusters of stars, or faint trails of debris left behind by the impact. Yet in Hubble's image, there were no such scars. The edges were clean, the stars were evenly distributed, and the galaxy looked too perfect to be the product of chaos. Because of this, many researchers began exploring other explanations, such as stable gravitational resonances or unusual patterns of matter that could hold such a delicate structure in place. Hubble did not solve the riddle of Hoag's object, but it did sharpen the puzzle. By showing the galaxy's clean lines and flawless geometry in such detail, it forced astronomers to admit how rare and extraordinary this structure truly is. Many theories that might have seemed reasonable before simply collapsed, because none of them could account for such perfection without leaving behind the marks of violence. And beyond the world of science, the picture had a cultural impact. It appeared in astronomy outreach programs, in school textbooks, and across online communities. People who had never cared much about galaxies before suddenly found themselves captivated by the image. Some were drawn in by its symmetry, others by its dreamlike beauty. For many, Hoag's object was the first time they realized that the universe is not only vast and mysterious, but also capable of producing natural objects that look as though they were crafted with an artist's hand. Hubble's photograph of Hoag's object became more than a scientific image. It became a symbol of wonder, a reminder that the universe hides shapes and patterns as surprising and as breathtaking as anything human imagination could design. The mystery of Hoag's object does not lie only in the dazzling golden core at its centre, or in the breathtaking ring of brilliant blue stars that encircle it like a cosmic crown. Instead, one of the deepest puzzles is hidden in something far less obvious, something invisible to the human eye but detectable through special instruments. This puzzle lies in the vast ghostly halo of gas that stretches around the galaxy, extending well beyond its outer ring. Unlike the bright lights that catch our attention in photographs, this halo is dim and elusive, yet it might hold the most important clues about the galaxy's history and its unusual nature. Scientists have discovered that this halo is made mostly of hydrogen gas, the simplest and most abundant element in the universe. What makes this discovery striking is not the mere presence of such a halo, because halos of gas are fairly common in galaxies, but the strange way this one behaves. To the naked eye, or even through an optical telescope, the halo cannot be seen at all. It is far too faint, like mist that evaporates before it is noticed. But when astronomers use powerful radio telescopes, which are able to measure the faint signals given off by hydrogen atoms, they can map out this hidden region. What they find is astonishing. The halo surrounding Hoag's object is unusually smooth, calm, and undisturbed, unlike the turbulent gas halos seen in most other galaxies. In many galaxies, particularly in galaxies that are actively producing new stars, the halo of gas is alive with motion. It is anything but still. There are streams of gas falling inward, feeding the central regions and fueling the birth of young stars. At the same time, other streams are being blown outward by fierce winds that come from exploding stars, powerful stellar eruptions, or even from the activities of a ravenous black hole at the galaxy's core. These push and pull processes, gas flowing inward to nourish star formation, and gas being blown outward by violent events, give halos a patchy, restless, and sometimes chaotic appearance. One can find areas where gas is compressed into dense knots, glowing brightly with potential starbirth, and other areas where it has been completely cleared away, leaving behind empty voids. But the halo of Hoag's object refuses to follow these rules. It does not behave like the energetic, boiling halos of other galaxies. Instead, it appears to be astonishingly calm, smooth, and almost frozen in place. When astronomers study the halo using spectroscopic techniques, which allow them to measure the Doppler shift of hydrogen's light, they find very little sign of motion at all. The gas is not rushing inward to feed the ring, nor is it being blown outward in violent gusts. It simply floats there, like a bubble of invisible mist surrounding the galaxy. This strange stillness is not only surprising but also deeply confusing, because it challenges what we know about how galaxies are supposed to work. The outer ring of Hoag's object is still producing new, young, and massive stars. These stars, which shine with the dazzling blue light of youth, require a constant supply of fresh, cold gas. Star formation is like a fire. Once the fuel runs out, the flames quickly die. For Hoag's object to continue making stars in its ring, there must be a steady flow of hydrogen gas feeding the process. But if the halo surrounding the galaxy is not actively sending gas inward, where is the ring getting its fuel? This is one of the most frustrating questions for astronomers who study the galaxy. The ring should not be able to sustain star formation on its own for such a long time without a steady supply. And yet somehow it continues to do so. Some scientists have suggested that perhaps gas is indeed drifting inward from the halo, but doing so in such tiny, delicate amounts that it escapes our ability to detect it. If this is true, it would mean the halo has found a remarkably stable way to deliver fuel to the ring without disturbing its calm, glass-like appearance. But this explanation only deepens the mystery. How could such a subtle and delicate process continue for so many millions of years without causing even a hint of turbulence? It would require a kind of cosmic balance that seems almost too perfect to believe. The sheer size of the halo adds yet another layer to the riddle. Estimates suggest that the halo extends 2 or even 3 times farther than the diameter of the bright visible ring of the galaxy. To put that into perspective, imagine the already enormous galaxy surrounded by a bubble of gas so vast that it makes the visible structure look small in comparison. This is an astonishing amount of space for a galaxy that appears to live in solitude, without close neighbours to feed it extra material. If Hoag's object is truly as isolated as it appears, then where did it acquire this enormous reservoir of hydrogen gas in the first place? Most galaxies that possess such large halos have gained them through encounters with other galaxies, by pulling in extra gas through tidal interactions, or by merging with smaller companions. But Hoag's object sits alone in the darkness of space, with no obvious donors nearby. The smoothness of the halo gives another clue about the galaxy's past. In many galaxies, especially those that have undergone violent encounters, the halos show scars of those events. There are streams of gas pulled out into long tails, shells of material left behind from collisions, or clumps where gas has been violently thrown together. None of these features appear in Hoag's object. Its halo seems pristine and untouched, suggesting that the galaxy has not experienced any major disruptions for hundreds of millions of years. This stability might be the reason the outer ring looks so perfectly symmetrical, because violent events usually warp, twist, or otherwise distort such structures. Yet, this same stability makes the galaxy far more difficult to explain, because most theories about how ring galaxies form involve some kind of disturbance, whether a collision, a merger, or a massive gravitational interaction. Some researchers have proposed that the halo might be a remnant left over from a much earlier stage of the galaxy's life. Perhaps long ago, when the ring first formed, a huge inflow of gas occurred. This gas could have come from a captured gas cloud drifting through space, or perhaps from the aftermath of a merger with another galaxy, or even from a resonance effect where the galaxy's own gravitational forces reorganized its gas. After the ring formed, the leftover material may have spread outward, forming the halo we see today. Over time, the chaotic motions within that gas would have settled down, leaving behind the calm and balanced structure observed now. This idea helps explain how such a large reservoir of hydrogen might exist around the galaxy. But it also raises another troubling question. If so much gas remains, why has more of it not fallen inward to feed the ring and create even more stars? The answer might lie in forces that are invisible to us, forces tied to the mysterious substance we call dark matter. Though we cannot see dark matter directly, we know it exists because of the way it shapes the movement of galaxies. In Hoag's object, the unusual behavior of the halo might be explained if the dark matter is spread in a very smooth spherical distribution. Such an arrangement would spread the galaxy's gravity evenly across space, preventing the gas from clumping or rushing inward too quickly. Instead, the gas could be held in a delicate balance, pulled inward by gravity yet kept outward by internal pressure. It would be like a perfectly balanced tug of war, with neither side fully winning. In this way, the halo might be frozen in its calm, glassy state by the silent hand of dark matter itself. The more we study Hoag's object, the clearer it becomes that its mysteries are not just about what we see with our eyes, the golden heart and the sapphire ring, but also about what we cannot see, the invisible forces and hidden gases that surround it. The halo of hydrogen may look quiet and uneventful, but it holds within it questions that reach to the very heart of how galaxies live, grow, and evolve. Is the ring being quietly fed by hidden rivers of gas too faint for us to detect? Did the halo form in the aftermath of some ancient event now lost to time? Or is it being held in its frozen state by the unseen influence of dark matter, creating a balance unlike anything we have observed elsewhere? In astronomy, when scientists talk about metallicity, they are not speaking of shiny metals like gold, silver, or iron in the usual sense that we imagine in everyday life. Instead, they use the word metals to mean all chemical elements heavier than hydrogen and helium. Hydrogen and helium are the most basic and abundant elements in the universe, and everything else, oxygen, carbon, nitrogen, silicon, iron, and beyond, is considered a metal by astronomers, no matter how ordinary or strange it might sound to us. The term might feel misleading, but in the language of astrophysics it is convenient. If a star or a gas cloud contains anything beyond hydrogen and helium, then astronomers call those extra ingredients metals, and the total amount of them is called the metallicity. The story of metallicity is really the story of the universe's gradual enrichment. In the beginning, right after the Big Bang almost 14 billion years ago, the cosmos was almost entirely made of hydrogen and helium, with just a trace of lithium. There were no heavier elements at all. Those came later when the first stars were born. Inside the intense furnaces of stars, hydrogen atoms are pressed together to form helium, and later on, as the stars age, new reactions make heavier elements like carbon and oxygen. In the most massive stars, the process goes even further, all the way up to iron. But the real explosion of metals into the universe comes when stars die. Some stars gently shed their outer layers, filling space with carbon and nitrogen. Others explode as brilliant supernovae, hurling iron, silicon, magnesium, and many other elements into the surrounding space. These stellar deaths enrich the galaxies with fresh metals, which then become part of new generations of stars, planets, and eventually life itself. Because this cycle has been going on for billions upon billions of years, astronomers can use metallicity as a kind of cosmic clock. Old stars, those that formed in the early universe, have very few metals, because they were born before many supernovae had had time to enrich their surroundings. Younger stars, on the other hand, usually contain more metals, because they form from gas that has been mixed again and again with the ashes of countless earlier stars. In most galaxies, this rule holds true. The oldest stars shine with a more primitive chemical mix, while the younger ones carry the fingerprints of multiple generations of stellar lives and deaths. But Hoag's object, the mysterious and unusually beautiful ring galaxy discovered in the 20th century, does not follow this neat and simple rule. This galaxy, with its golden central core and almost perfectly circular outer ring of bright blue stars, challenges astronomers in many ways, and metallicity is one of the biggest puzzles it presents. When scientists studied the chemical makeup of the young blue stars in the outer ring, they expected those stars to be relatively metal-rich, because their youth suggested that they were born from gas that had already been enriched by the older core. But to their surprise, the stars in the ring turned out to have significantly lower metallicity than the stars in the central core. Their composition looked more like gas that had come from somewhere else entirely, gas that had followed a very different evolutionary path. It was as if the stars in the ring had been made not from the enriched leftovers of the galaxy's own history, but from gas that belonged to another environment altogether. This was a shocking result, because if the ring had been created simply by pushing the galaxy's own internal gas outward, for example through a collision, a burst of energy, or some internal reshaping, then the gas in the ring would have had the same chemical fingerprint as the gas in the core. The stars would have shared the same metal content, but they did not. Instead, their lower metallicity hinted at an external origin. Something from beyond Hoag's object had apparently provided the raw material for the ring. One possible explanation is that Hoag's object somehow managed to capture a massive cloud of nearly pure hydrogen gas from the vast spaces between galaxies. The universe is not entirely empty in those regions. Enormous clouds of almost pristine hydrogen still drift there, leftovers from the early universe that never quite condensed into galaxies. If Hoag's object swept up such a cloud, it could have fueled the creation of the outer ring. This scenario would naturally explain why the ring stars are still forming and why their metallicity is lower than expected. They were born from fresh gas that had not gone through many previous generations of star formation. Yet there is a problem with this idea. Capturing such a large quantity of gas is not simple. Normally, when galaxies interact strongly enough to grab material from one another or from the intergalactic medium, they leave behind messy signs, tidal tails, streams of stars, asymmetric shapes, or scattered debris. Hoag's object, however, looks almost eerily perfect. Its outer ring is smooth, symmetrical and circular, not ragged or uneven as one might expect from a violent capture. There are no obvious scars that would tell us it went through a cosmic struggle to pull in so much gas. The lack of disorder makes this explanation hard to accept, at least without some unknown mechanism that could allow for a perfectly calm capture of a giant cloud. Another idea is that the ring could be the remains of a small gas-rich dwarf galaxy that Hoag's object swallowed long ago. In this picture, the dwarf galaxy's stars might have been too faint to survive clearly, but its gas settled into a ring around the larger galaxy's core and then began to form new stars. This theory would also make sense of the lower metallicity, because dwarf galaxies generally contain less metal than large ones. If Hoag's object consumed such a dwarf, the metallicity of the resulting stars in the ring would match what we see. But this explanation too has weaknesses. If a merger had really happened, astronomers would expect to see some traces of it. Perhaps leftover stars from the dwarf scattered around, or distortions in the ring's shape. But the ring of Hoag's object is unusually perfect, almost impossibly so. It lacks the irregularities and clumps that usually mark the aftermath of a galactic meal. Moreover, no clear signs of the dwarf stars have been detected. Without that evidence, the merger idea feels incomplete. The puzzle deepens when we look more closely at the metallicity within the ring itself. In many galaxies, metallicity varies across different regions. There may be gradients, with more metals near the centre and fewer in the outskirts, or patchy differences caused by uneven star formation, supernova explosions and inflows of gas. But in Hoag's object, the metallicity of the ring appears strikingly uniform all the way around. It is as if the gas was perfectly mixed before any stars began to form. This level of chemical evenness is difficult to explain. Normally, thorough mixing of gas requires turbulence or rotational flows, processes that stir the material violently and spread elements evenly across wide regions. But the outer ring of Hoag's object shows no sign of being shaken up in such a way. Its stars are arranged smoothly and symmetrically, not chaotically. This suggests that the gas settled into the ring very gently, without the kind of high-energy drama that is usually associated with ring formation. Once again, the observations clash with the standard explanations. There is also another subtle but important detail. While the stars in the ring clearly have lower metallicity than those in the golden core, they are not completely metal-free. They contain oxygen, nitrogen, iron, and other heavy elements at significant levels. This tells us something crucial. The gas that formed the ring was not entirely primordial. It had already been through at least one round of star formation somewhere, sometime, before it found its way into Hoag's object. In other words, the gas is not untouched material from the Big Bang. It has a history. The mystery, then, is whose history it was, and how that history ended up surrounding the galaxy in such a strange, perfectly circular arrangement. This raises questions about the timeline of Hoag's object. The difference in metallicity between the core and the ring suggests that they may have formed at very different times, perhaps even under very different conditions. The golden central core could have formed early in the history of the universe, billions upon billions of years ago, and then stabilized without much new star formation. It could have held onto its higher metallicity population while using up or losing much of its gas. Later, a fresh supply of lower metallicity gas might have arrived from outside, settling into the neat ring we see today and sparking new star birth. This possibility would mean that Hoag's object has two distinct histories hidden within it. The core tells the tale of the galaxy's ancient past, when it first condensed and built up its older metal-rich stars. The ring, on the other hand, tells a more recent story, one in which new material arrived from beyond and created a younger generation of stars with a very different chemical fingerprint. The contrast between the two components, the old golden heart and the young blue halo, embodies a deep and unresolved cosmic mystery. Astronomers are left with tantalizing clues but no definitive answers. The metallicity of Hoag's object refuses to fit into the standard patterns. It hints at processes that are gentle yet powerful, foreign yet intimately tied to the galaxy's fate. It suggests that galaxies are not always self-contained systems, but can sometimes be transformed by gifts of gas from the larger universe. At the same time, the lack of scars, distortions, or leftover debris makes the story harder to piece together. It is like finding a beautifully carved artifact in an archaeological dig, without any trace of the tools or workshop that might have created it. The metallicity puzzle of Hoag's object therefore remains one of its most intriguing mysteries. It is not simply a question of numbers and chemical ratios. It is a window into the hidden dynamics of galaxy evolution, the invisible exchanges of matter between galaxies and the cosmos around them, and the quiet processes that can sculpt something as astonishingly symmetrical as this galaxy's ring. For now, the young blue stars in the ring and the old golden stars in the core shine together, side by side yet profoundly different, reminding us that even the most beautiful objects in the sky can carry secrets that challenge everything we think we know about the universe. The mystery of Hoag's object grows even deeper when scientists look at how it spins. In most galaxies, whether they are spirals or ellipticals, the inner regions and the outer regions tend to move in harmony. For spiral galaxies, the bright bulge at the center and the graceful arms that curl around it usually turn at nearly the same pace, locked together in a common rhythm. In elliptical galaxies, which lack arms and instead form glowing ovals or spheres, the whole structure drifts as one giant system, though it does so in a less tidy and less organized fashion. But Hoag's object does not follow this familiar rule. It refuses to behave like other galaxies. In this strange system, the golden heart at the center and the shining blue ring that surrounds it rotate at very different speeds. Astronomers have measured the way the light from its stars stretches and compresses because of the Doppler effect, and the results were astonishing. They revealed that the stars in the ring are moving around the galaxy much faster than the stars in the core. In fact, the core itself seems to rotate only sluggishly, while the outer ring spins with the speed and liveliness of a fully developed disk galaxy. It is almost as though the galaxy's heart has grown tired and slow, while the shell around it has kept its energy and vigor. This difference in movement is not a small detail. It carries with it a message about the history of Hoag's object. If the ring had formed naturally as part of the core's own disk, then their motions would be tied together. The central mass would act as the anchor, setting the pace for the surrounding material. Yet the faster spin of the ring suggests it is not obeying the commands of the core at all. Instead, it may be dancing to the pull of a much larger and unseen structure, the galaxy's dark matter halo. In this picture, the golden center plays only a minor role, while the vast invisible web of dark matter dictates the graceful motion of the outer ring. This leads to another intriguing possibility. The central core, with its slow turn, may be the faded remnant of an old elliptical galaxy, one that formed long ago and now drifts with only the faintest spin. Later, perhaps by capturing a great store of gas from outside, this old galaxy could have grown a ring of fresh material. The new gas, guided by the stronger pull of the dark matter halo, began to spin rapidly and to form the glittering blue stars that shine today. In this way, the difference in speeds between the slow golden center and the swift blue ring would make perfect sense. What is even more remarkable is the clean boundary between these two regions. In many galaxies that contain mismatched parts, there is a kind of messy zone where the motions clash. Stars get twisted into unusual paths, structures warp, and chaos appears. But Hoag's object has none of that. Between the glowing heart and the brilliant ring lies a wide empty gap, almost like a moat, which keeps the two systems from interfering with each other. Because they are not physically touching, their movements remain separate, and the core has not been able to pass its slow rotation onto the ring. Astronomers also point out that the slow spin of the golden core may explain why it looks so clean and dust-free. In many galaxies, flows of gas gradually spiral into the core over billions of years, feeding its stars and giving it a faster spin. But in Hoag's object, almost all the available gas lies far out in the blue ring and the invisible halo. The heart has been left alone, cut off from fresh fuel, and so it has been evolving very quietly, very slowly, for a long time. This sluggish motion may also reveal something about the central black hole, if one exists there. In many galaxies, the spin of the core helps funnel gas into the very center, where it feeds the black hole and triggers eruptions of energy that shine across the universe. But in Hoag's object, the core seems too still and too quiet to provide such fuel. Observations in radio waves and X-rays show little to no activity. The black hole, if it is there, seems to be starving, left without the steady diet of gas that makes other galactic hearts flare so brightly. One of the lingering mysteries is whether the golden core has always been this slow. Perhaps the difference is only temporary. If the ring was added only within the last billion years, a short time on the cosmic clock, then there has not yet been enough time for the two systems to adjust to each other. Over the next several billion years, the slow heart and the fast shell may gradually tug on each other, slowly bringing their speeds closer together. If that is the case, then we may be witnessing Hoag's object in a rare and fleeting moment, a galaxy caught halfway between two different states of being. The galaxy's solitude may also play a role. Unlike galaxies in crowded clusters which often bump, pull and disturb each other, Hoag's object drifts alone in a quiet stretch of space. With no neighbours to jostle it, the strange separation between core and ring could last for ages, perhaps even forever. It may remain preserved like a fossil, a living relic of how galaxies once were, wrapped in a glowing shell that continues to burn brightly with young stars. But if the strange motion of the core is one puzzle, the activity of the ring is another. That outer ring is not quiet at all. It is bursting with new stars, shining with the brilliant blue light of young giants. These are O-type and B-type stars, the kind that live fiercely and die young, often in just a few million years. Their short lives mean that the ring is constantly replenishing its population, creating stars over and over again. Usually such bursts of star formation happen when something dramatic has occurred. A smaller galaxy crashes into a larger one, compressing its gas into dense clouds that suddenly ignite with new suns. Or a close encounter between galaxies stirs up tidal forces that push gas inward and trigger furious starbirth. Yet in Hoag's object, none of these familiar triggers are present. The galaxy shows no scars of collision, no streams of scattered stars, no warped shapes. It floats in peace, far away from any likely intruder. Even the small background galaxy that appeared near it in the famous Hubble image lies far behind and is not connected to it in any way. So what is driving this steady storm of star-making in the ring? One idea is that the gas has been there for billions of years, slowly gathering and only now becoming dense enough to form stars. But if that were true, the supply should be dwindling by now, and the starburst should be slowing down. Instead, the star formation is spread smoothly and evenly all around the ring, suggesting that the gas is somehow being replenished or kept in balance. Some astronomers think the ring might be a self-sustaining machine. As new stars are born and then explode as supernova, they send shock waves racing through the gas. These waves could trigger more stars to form nearby, creating a cycle that feeds itself endlessly. If the ring's structure channels these waves around its edge, it could maintain a steady loop of star-making without any need for outside help. Another clue lies in the chemical makeup of the stars. The ring stars have low metallicity, meaning they contain fewer heavy elements than expected. This suggests that the gas in the ring either came from a relatively untouched, pristine source, or was drawn in from beyond the galaxy itself. Gas with few heavy elements does not collapse into stars very easily, so the fact that the ring is full of young stars makes the situation even more mysterious. It is as if the galaxy has somehow found a secret way to coax reluctant gas into producing stars at just the right pace. The dark matter halo may again be the key. If the invisible halo around Hoag's object is unusually smooth and round, it could provide a stable gravitational stage where gas can circle calmly without being disturbed. Gentle ripples or waves within the ring might occasionally compress the gas just enough to ignite new stars. This would be a quiet, graceful process, far different from the violent crashes that create starbursts in other galaxies. There is also a more daring idea. Perhaps the ring is being stirred by something we cannot see. A tiny companion galaxy, too faint for our telescopes to detect, could be slipping through the ring, sending out ripples as it passes. If such an intruder exists, it must be extremely small and aligned almost perfectly, so that it leaves the ring's perfect symmetry untouched. The graceful and almost magical ring of Hoag's object might have been born through something called orbital resonance. This idea is one of the most fascinating explanations ever suggested for how this perfect circle of stars came to be. To understand it, we need to picture how objects in space can sometimes move together in a special rhythm. In a galaxy, the paths of stars, great clouds of gas, and even smaller nearby galaxies can sometimes influence one another so strongly that their movements lock into a kind of cosmic harmony. This is what astronomers call a resonance. When resonance happens, matter is no longer spread out evenly. Instead, it is guided and pushed into certain places, leaving behind empty spaces in other regions. These patterns can appear as rings, gaps, or arcs. We already see this clearly within our own solar system. The beautiful rings of Saturn, for example, are carved and shaped by the gravitational pull of Saturn's many moons. Some moons nudge the icy particles into clusters, while others sweep gaps clean. In the end, what we see from afar is a perfect set of shimmering rings, all born from this mysterious dance of resonance. When scientists take this idea and apply it to galaxies, they often find that resonant rings are created by bars of stars or spiral arms deep inside the galaxy. These structures, which rotate like gigantic stirring spoons, pull on the surrounding stars and gas at regular intervals, the way a repeated push can make a child's swing go higher and higher. Over countless millions of years, matter piles up at special orbital distances where the motion of the stars matches the rhythm of the rotating bar or spiral. In those regions, a glowing ring of stars and gas can form and remain stable for a very long time. But here lies the riddle. Hoag's object does not have any of those usual features. It does not have a bar of stars at its core. It does not have spiral arms stretching outward. At its centre, there is nothing more than a smooth, dust-free golden sphere of stars, calm and featureless. If resonance requires a driver like a spiral or a bar to get started, then Hoag's object is missing the very thing that would normally make the process work. This is why astronomers have suggested that perhaps the resonance was not caused by something inside the galaxy at all, but by something outside it. Maybe, a very long time ago, a smaller galaxy drifted nearby. Its gravity might have tugged at Hoag's object just enough to set the stars and gas into a resonant pattern, one that eventually blossomed into the circular ring we see today. If that happened, the smaller galaxy has long since vanished into the dark, leaving only the ghostly trace of its passing behind, a hauntingly perfect ring as silent evidence. This idea has been nicknamed ghost resonance. It is a clever solution because it does not need a permanent bar or spiral pattern, but it is also a frustrating one. The culprit is gone, and so proving it is almost impossible. Others have suggested that the answer might lie in something even stranger: dark matter. Every galaxy, including Hoag's object, is thought to sit inside an invisible halo of dark matter. We cannot see it, but we know it is there because its gravity shapes the movements of stars and gas. If the dark matter halo around Hoag's object has a slightly uneven density, or some strange shape, it could subtly guide the orbits of stars until they gathered into a ring. In this sense, the hidden skeleton of the galaxy might be the true artist behind the masterpiece. Since dark matter is invisible, it is often the place scientists look when all ordinary ideas fail. Still, the resonance theory faces a stubborn challenge. Rings formed this way usually look a little messy. They tend to have brighter clumps here and there, where bursts of new stars are forming. Their thickness can vary, sometimes wide in one part and narrow in another. But the ring of Hoag's object is nothing like this. It is smooth, unbroken, and so perfectly even that it almost seems artificial. If resonance is behind it, then it is doing something in Hoag's object that we have never seen anywhere else in the universe. Even powerful computer models struggle to create anything this flawless. When astronomers set up a simulation with a smooth central core and attempt to form a ring through resonance alone, the outcome is usually lopsided or warped, not a perfect circle. To get something like Hoag's object, the initial conditions in the model have to be tuned with almost impossible precision, as though the universe staged a once-in-a-billion performance. That makes some scientists wonder if this is not just a rare example of resonance, but perhaps the only one of its kind ever to exist. And yet, there is one part of the resonance story that fits beautifully: stability. When stars and gas are locked into resonant orbits, they can stay there for billions of years. They avoid collisions, they avoid scattering, and they hold their positions relative to one another like dancers moving in step. This could explain why Hoag's object has kept its shape for so long. Even without recent disturbances, the ring may simply be locked in a timeless rhythm, preserved by the very harmony that created it. What astronomers lack is direct proof. They would need to measure the motions of the stars in the ring and see if they match the predictions of resonance. Perhaps one day, when telescopes more powerful than Hubble are pointed at Hoag's object, such a pattern will be found. Until then, resonance remains a possibility without a smoking gun. If it really is resonance, then Hoag's object might be the most extreme, and perhaps the only, example of such perfection in the entire universe. That makes the mystery even deeper. We might have to accept that one of our best ideas does not fully explain it, and that nature has played a trick on us, crafting a galaxy ring more perfect than theory should allow. When Hoag's object was first discovered around the middle of the 20th century, astronomers thought they had a simpler answer. Maybe it was not a strange galaxy at all, but merely an illusion. They wondered if what we were seeing was a trick of light called gravitational lensing. This happens when a massive object, such as a galaxy cluster, bends and magnifies the light of another object far behind it. Sometimes, if everything lines up perfectly, the light forms a glowing ring around the closer object. This phenomenon is known as an Einstein ring. At first glance, Hoag's object looked exactly like one, a golden ball of light in the middle, surrounded by a perfect circular ring. It was a tempting explanation. Perhaps the golden core was just an ordinary nearby galaxy, while the ring was really the stretched and bent light of a distant background galaxy. That would have been neat, simple, and elegant. No mysterious formation scenarios needed. But when scientists studied Hoag's object in more detail, this theory began to collapse. The first evidence came from spectroscopy. By splitting the light of the core and the ring, astronomers could measure their redshifts, the telltale stretching of light that shows how far away an object is. To everyone's surprise, the ring and the core had the same redshift. They were not two separate galaxies at different distances, but two parts of the very same structure. Then there was the ring itself. Real gravitational lenses usually smear and distort the images they produce. You often see arcs, repeated shapes, or faint streaks. But the stars in Hoag's ring were sharp, clear, and evenly distributed, as though we were looking directly at them. There was no distortion, no warping, no doubling of images. Another problem was mass. To bend light into such a large and perfect ring, the lensing object in the centre would need to be enormously massive, much larger than Hoag's object's small, smooth core. Usually only giant galaxies or whole clusters, wrapped in enormous halos of dark matter, can produce clean Einstein rings. Hoag's object's modest heart simply does not have the strength to perform such a trick. And then there was the gap. In an Einstein ring, there is no reason for the space between the core and the ring to be perfectly empty. Light can spill inward and fill that area with faint images. But in Hoag's object, the gap is silent and dark, a true void with no stars at all. This emptiness makes sense if the ring is real, but not if it is a lensing illusion. Finally, astronomers observed how the ring itself rotates. Its stars are not drifting separately, as they would if they belonged to a background galaxy. Instead, their motions are tied to the central core by gravity. The two are bound together, moving as parts of a single system. This fact alone sealed the fate of the lensing idea. By the time the Hubble Space Telescope captured Hoag's object in the year 2002, the lensing theory was already dead. The crisp details of the Hubble image showed the ring filled with evenly scattered clusters of stars, and even revealed a distant twin galaxy far behind Hoag's object that looked exactly like a lens system should. The contrast was unmistakable. Hoag's object was no illusion. It was a galaxy with a structure unlike any other we had ever seen. When astronomers study galaxies, they do not just look at them with their eyes, or even through telescopes that capture visible light. They also listen to the universe in another way, by using radio telescopes. Radio waves reveal hidden things that ordinary light cannot show. They can uncover how stars are born deep inside thick clouds of dust, how giant black holes send out powerful jets of energy like cosmic lighthouses, and how the faint whisper of a neutral hydrogen gas spreads across galaxies like a background hum. Many ring-shaped galaxies glow strongly in radio waves. This brightness often comes from rapid bursts of starbirth happening inside them. In such galaxies, huge clouds of gas collapse, forming massive stars. These stars live fast and die young, exploding as supernovae and filling their galaxies with energy, radiation, and cosmic rays. The chaos of these events produces powerful radio signals, making such galaxies roar in the radio part of the spectrum. But Hoag's object does not roar. It barely even whispers. When astronomers pointed their radio telescopes toward Hoag's object, they found something surprising. Instead of the loud signals expected from an active star-forming ring, they only picked up the faintest traces of radio waves, so weak that they hovered just above the limit of detection. This was astonishing, because the bright blue ring around Hoag's object shows many young massive stars, exactly the kind of stars that should be exploding as supernovae and filling the galaxy with radio energy. Normally, these massive stars end their lives in brilliant explosions, hurling out cosmic rays that spiral along magnetic fields and shine as synchrotron radiation. This radiation is one of the clearest signatures of intense starbirth. Yet in Hoag's object, the expected signal is missing, or at least reduced to a near silence. Why is this galaxy so quiet in radio waves? One possible reason is that the rate of massive star formation is lower than it appears in optical images, but that seems unlikely, because the vivid blue colour of the ring clearly shows the presence of many hot, short-lived stars. A second explanation is that supernovae inside this galaxy are somehow less efficient at creating cosmic rays, and yet another idea is that something about the galaxy's environment is interfering with the usual chain of events that turns explosions into radio light. One particularly interesting theory is that Hoag's object might have a much weaker magnetic field than most galaxies. In normal galaxies, cosmic rays released by supernovae spiral along the lines of magnetic fields, lighting up in radio waves as they move. But if the magnetic field is weak, fewer cosmic rays get trapped, and the overall radio brightness drops sharply. Measuring magnetic fields in galaxies is extremely difficult, but Hoag's object could serve as a striking example of how these invisible forces shape the radio voice of a galaxy. Another idea is that the gas inside the ring is spread out in an unusual way. In galaxies where star formation is bursting at full speed, thick and clumpy clouds of gas and dust act like a net, keeping energetic particles from escaping. These particles then bounce around, giving off stronger radio signals. But if Hoag's object's gas is more evenly spread out, the particles might escape into the vast darkness of intergalactic space before they can radiate much energy. This would explain not just the weak radio signals, but also other odd features of the galaxy, such as the straight ribbon of gas in its halo and the calm, almost motionless appearance of the ring. The silence extends even deeper into the galaxy's very core. In most galaxies, even those that are not particularly active, the central black hole usually produces at least some radio energy. It might come from hot gas swirling around the event horizon, or from weak jets of material being pushed outward. But in Hoag's object, there is no sign of such activity at all. Its core appears unusually quiet and passive, matching other clues like its slow rate of rotation and the absence of dust lanes or gas flowing inward. Even the hydrogen line emissions that astronomers normally use to trace cold gas in galaxies are faint here. This does not mean that Hoag's object lacks gas. Other studies confirm that it does have a large halo of hydrogen. But this gas seems to be spread too thinly or too smoothly to create strong localized signals. Once again, the impression is of a galaxy where everything is calm, evenly distributed and almost static. From a broader point of view, this radio silence adds another layer to the mystery of Hoag's object. It is not only strange in visible light, with its perfect golden core and flawless blue ring, it is also strange in radio waves. Most galaxies that look as unusual as this one also sound unusual when studied with radio telescopes. This is because the forces that twist galaxies into strange shapes, collisions, mergers, or violent gravitational interactions, usually also produce loud bursts of radio energy. But Hoag's object seems different. Whatever created it must have been a rare, peaceful event, or perhaps something that happened so long ago that all the energetic echoes have long since faded away. In the future, more powerful instruments will be able to probe this mystery in finer detail. One of the most promising tools is the Square Kilometre Array, a giant radio telescope project that will be able to make extremely sharp maps of galaxies like Hoag's object. Even then, astronomers expect to find only faint whispers of radio energy from this system. If those predictions hold true, Hoag's object will stand as one of the universe's quiet masterpieces, a galaxy that values stillness over spectacle, a cosmic jewel that shines in silence. The shining golden heart of Hoag's object is not just special because of its warm colour, or because it turns ever so slowly. What makes it even more striking is how spotless and perfectly smooth it looks. Most galaxies, even the calm and rounded elliptical ones, usually carry scars and blemishes at their centres. These small imperfections might appear as thin lanes of dust cutting across the core, faint streams of drifting gas, or scattered clusters of stars resting on the surface like tiny islands. They are like old wrinkles and marks that tell the long story of galactic life, of collisions, gas flows, and slow transformations that stretch across billions upon billions of years. But when astronomers turn their eyes to Hoag's object, they see something very different. Its golden sphere in the middle is so pristine that it feels almost unsettling, as though nature has deliberately polished it to perfection. When the mighty Hubble Space Telescope captured the galaxy in the year 2002, its sharp vision was powerful enough to reveal even the tiniest details across the core. Scientists expected to find the usual patterns of brightness, patches that hint at dust clouds, knots of newborn stars, or faint traces of younger generations hiding inside the glow. Instead, they discovered something astonishing. The light from the core is almost perfectly uniform, glowing like a flawless golden orb of ancient stars. There are no strands of dust cutting across it, no blue sparks of fresh stars, no tangled knots of recent activity. It is as if the core has been sealed off in silence for countless ages. This level of purity is rare, because galactic cores are usually messy and restless places. Over time, gas from the outer regions of a galaxy tends to drift inward under the pull of gravity. When that gas settles in the centre, it often triggers fresh bursts of starbirth, or awakens a sleeping black hole with new fuel. Dust gathers along the way, shaping dark lanes or swirling clouds that break up the light, leaving the signature textures that astronomers expect to see. Even galaxies that are not merging with others still get disturbed by the pull of passing neighbours, small satellite galaxies that can tug at the heart and leave behind uneven traces. The fact that Hoag's object shows none of these common features is extraordinary. It suggests that its golden heart has lived in an unusual state of long-lasting peace and isolation. The smoothness also strengthens the idea that this core is made up almost entirely of ancient stars. Spectroscopic studies show that its light is mostly yellowish, the same shade often found in old, fading stars that fill elliptical galaxies. If no fresh gas has fallen into the core for billions of years, then no new stars would have been born there. What remains is simply the ancient population, spread evenly across space, glowing together like a timeless relic. Yet the real mystery is not just that the core is old, it is that it has remained untouched for so long while a lively ring of star formation spins all around it. In most galaxies, material from an active star-forming disk tends to slowly drift inward, pulled by gravity, until it eventually falls into the central regions. But in Hoag's object, there is a vast, haunting gap of emptiness between the glowing core and the bright blue ring. This hollow space acts almost like a protective barrier, keeping the gas outside and stopping it from ever reaching the centre. Without that inward flow, the core has been locked away, preserved almost exactly as it was in its earliest days. Some people might wonder whether this smoothness is simply an illusion, an optical trick caused by the angle from which we see it. If we happen to be looking straight down the galaxy's axis, perhaps we might miss certain details that would be visible if seen from the side, but the near-perfect symmetry of the outer ring makes it very likely that we are viewing Hoag's object almost exactly from the side. That means the smoothness of the core is real, not just a trick of perspective. Another possibility is that the heart of Hoag's object went through a violent past, one so intense that it wiped the slate clean. Perhaps powerful winds from exploding stars, supernovae, or an earlier, more active black hole once swept through, blasting away every last trace of dust and gas. Such a storm could have left behind only the stars, shining undisturbed in the aftermath. Over billions of years, the chaos would have faded, leaving behind the calm, even glow we see today. But if such an event did happen, it should have left scars, remnants like shells of ejected gas, or rippling shock fronts carved into space. Yet we see none of those telltale signs. The silence is too complete. This uncanny smoothness is not just something beautiful to look at, it is a scientific clue. It tells us something profound about how this galaxy formed and how it has lived its long life. A heart this flawless could only have come about in one of two ways. Either the galaxy's formation was extraordinarily gentle and quiet right from the beginning, or some ancient event smoothed away every rough edge with unimaginable precision. Both ideas challenge the usual models astronomers rely on, because according to those models, a galactic core should almost always bear some sign of disturbance. And so, the golden heart of Hoag's object stands as one of the universe's most intriguing riddles, a smooth, shining sphere untouched by time, glowing with the light of stars that were born long before Earth itself came to be. From far away, the outer ring of Hoag's object looks like a perfect racetrack drawn across the sky, as if some cosmic hand traced it with flawless precision. It is a bright, smooth loop made of countless stars and clouds of glowing gas, and from our perspective it seems frozen in place, unmoving and timeless. But this calm appearance is misleading. Rings like this are not just pretty decorations floating in space, they are alive with motion and tension. Every single star in the ring is racing at hundreds of kilometers each second around the golden heart of the galaxy. These dizzying speeds are not random, they are what keeps the balance of gravity just right, holding the ring together in a fragile harmony. The great puzzle is this: how can such a vast and delicate structure stay intact for billions of years without breaking apart, fading into disorder, or collapsing into an ordinary galactic disk? In most galaxies, especially elliptical ones, the outer stars lie in a broad, flat disk. They are held steady by the combined pull of the visible matter, the stars, the gas, and the dust, as well as by an even greater invisible force, a ring of dark matter that surrounds the galaxy. In a galaxy shaped like a ring, however, the problem is trickier. In Hoag's object, there is a vast empty gulf between the glowing blue ring and the golden core. That emptiness means the ring is not supported by a continuous spread of stars lying inside it. Without some other invisible stabilizing influence, gravity alone should have tugged the stars closer to the core or pushed them farther away, gradually smearing the ring into something shapeless. One of the main stabilizing forces appears to be the galaxy's dark matter halo. Observations suggest that Hoag's object is wrapped in a massive, nearly spherical halo of dark matter, stretching far beyond the visible ring itself. This invisible envelope acts like a hidden skeleton, providing a gravitational framework that holds the stars of the ring in place along smooth, nearly circular paths. If this hidden mass were not there, the ring would probably dissolve in just a few 100 million years, an eye blink compared to the billions of years that galaxies usually survive. Another clue lies in how evenly the ring rotates. Astronomers measure this by studying the Doppler shifts of stars and gas around the ring, a technique that reveals their orbital speeds. In most galaxies with rings, small differences in speed eventually cause clumps, warps or cracks in the structure. Yet in Hoag's object, the stars and gas all seem to move with astonishing uniformity, as if guided by an unseen conductor. This unusual smoothness may be the result of the galaxy's halo and core being almost perfectly balanced in how their mass is spread out. Such symmetry would create a gravitational field that keeps the orbits lined up neatly, allowing the ring to remain stable and almost perfectly circular. Gas also plays its part in this cosmic dance. The ring is not made only of stars, it also contains large amounts of gas. Unlike stars, gas clouds can collide, merge and bleed off energy, gradually settling into a common orbital plane. This process smooths out irregularities and helps the ring maintain its graceful shape, even when individual stars wander slightly from the ideal paths. Normally, though, gas clouds tend to drift inward over time, feeding the core and filling the empty center. Yet in Hoag's object that has not happened on any large scale, the golden heart remains almost untouched, as if the ring is stubbornly refusing to let go of its gas. Some astronomers believe the answer may lie in the self-regulating nature of star formation within the ring. Whenever new stars are born, they unleash powerful winds and later in their lives the colossal blasts of supernovae. These energetic outbursts stir the gas and push it around, preventing it from clumping too tightly in one spot. Instead, the gas remains spread evenly around the circle. This delicate balance could explain why star formation is distributed so smoothly, and why the ring remains thin and elegant instead of thick and chaotic. In this sense, the very stars of the ring may act as its guardians, maintaining its stability through their births, lives, and deaths. Another striking fact is how narrow the ring is compared to its overall diameter. The width of the ring is only a fraction of its size, meaning the stars and gas clouds follow orbits that are extremely well aligned. In many other galaxies, nearby objects or neighbouring galaxies tug at stars through gravity, gradually thickening or distorting such structures. But Hoag's object is remarkably isolated, far from strong gravitational neighbours. Its great distance from other galactic systems may be its best shield, protecting its perfection from outside interference. And yet, even with all these stabilizing influences, there is still a mystery. When astronomers run computer simulations of galactic dynamics, they rarely produce a ring like Hoag's object that can survive for billions of years. In most models, the ring either collapses inward, forming a disk, or slowly breaks apart into a messy and irregular halo of stars. That Hoag's object still exists, so pristine and symmetrical, suggests it may have been born under unusually favourable conditions. Perhaps from the very beginning it had a perfectly balanced distribution of dark matter, gas, and stars. Perhaps nothing has disturbed it since then, leaving it to circle endlessly in serene perfection. Seen this way, Hoag's object is more than just a curiosity. It is a rare and almost miraculous survivor, a cosmic racetrack that has held its form across billions of years of galactic history. Its symmetry and endurance whisper of hidden forces and delicate balances that astronomers are only beginning to understand. A silent riddle carved into the fabric of the universe itself. In today's astronomy, computers are almost as important as telescopes. Astronomers no longer just look at the sky through lenses, they also build virtual versions of galaxies inside powerful machines. These computer-made galaxies, called simulations, are like giant laboratories where scientists can test their ideas about how the universe works. Into these models they pour the known rules of physics, the pull of gravity, the drifting of gas, the power of radiation, and even the mysterious influence of dark matter. With these tools, they can make galaxies twist, collide, shine, or even tear themselves apart in ways that closely resemble what we see through telescopes. Over the past 20 years, these models have become so advanced that they can now recreate many of the most striking features of galaxies. They can build swirling spiral arms that stretch across thousands of light years. They can show violent starburst regions where newborn stars erupt out of clouds of gas. They can even mimic ring-like shapes that appear when galaxies crash together, sending shockwaves rippling through space. For many galaxies, the match between what is simulated and what is observed is surprisingly good. But then there is Hoag's object. This strange, lonely galaxy refuses to cooperate. The biggest stumbling block is its breathtaking symmetry. When scientists try to reproduce it in their computer models, the results always fall short. No matter how advanced the resolution, the simulated rings usually come out slightly oval, tilted or broken into clumps. This would be acceptable for most galaxies because the real universe is messy. Stars and gas are constantly tugged at by gravity from nearby companions, hidden structures, or even the galaxy's own inner parts. Small irregularities are expected, almost inevitable, and yet Hoag's object defies this. Its ring is a flawless circle, so perfect that even the most precise computer programs cannot match it without cheating by smoothing out the data. The ring looks as though it was drawn with a compass, and that perfection makes it one of the hardest puzzles in astronomy. Another mystery lies in the space between the golden central core and the blue outer ring. In most galaxies, this gap never stays empty for long. Over hundreds of millions of years, gravity usually pulls some gas and stars inward, filling the void and sparking new star formation closer to the center. In galaxies like the famous Cartwheel Galaxy, bridges of gas and dust stretch between the ring and the core, feeding material inward. But Hoag's object does not play by these rules. The gap remains eerily clean and nearly empty of stars, as though something is protecting it. In computer models, however, the gap vanishes quickly unless very special conditions are forced into the equations. Theories of how the galaxy was born also face difficulties. One popular idea is that Hoag's object formed after a smaller galaxy punched straight through a larger one. Such cosmic collisions are known to produce rings, much like ripples in a pond when a stone is thrown in. And indeed, models of these encounters do produce ring galaxies, but not ones like Hoag's object. The simulated galaxies usually end up with scattered debris, uneven arcs, or warped structures, none of which we see in the real object. Another idea suggests that internal resonances, the synchronized motions of stars and gas, could have gathered material into a ring. Many galaxies with central bars use this process to form rings around the bar, but Hoag's object has no bar at all, and removing the bar from the equations makes the math shaky. Even when scientists try to adapt the models, the resulting rings tend to wobble, fall apart, or fade away after a while. Gas chemistry only deepens the puzzle. The stars in Hoag's object's ring have a chemical makeup that does not neatly match any of the expected sources. If the ring formed from the galaxy's original gas, its metallicity, the amount of heavy elements beyond hydrogen and helium, should be one way. If the ring came from gas pulled off a smaller companion, its metallicity should be another way. But in Hoag's object, the numbers are inconsistent with either scenario. When astronomers include these metallicity details in their models, the odds of producing a ring that looks like Hoag's object shrink to almost nothing. Dark matter, the invisible glue that shapes galaxies, adds yet another layer of difficulty. The way a galaxy's dark matter halo is distributed, its shape, density, and smoothness, decides whether delicate structures like rings can last. Adjusting the halo in computer models can sometimes make a Hoag-like ring stable, but then something else breaks. A dense halo that locks the ring in place might also make the central core spin too quickly, or it might trigger too much star formation in the middle, leaving behind dust and uneven features that are completely absent in Hoag's object. Even the most sophisticated modern simulations, the kind that combine gravity, starbirth, supernova explosions, and the galaxy's wider environment, fail to capture everything at once. Some models manage to make a convincing circular ring, but then the core comes out lumpy. Others can create a smooth golden core and a clean central gap, but the ring becomes slightly stretched like an ellipse. Every attempt seems to end with a trade-off, as if Hoag's object is daring the laws of physics. Match me, if you can. This ongoing failure does not mean astronomers are wrong about how galaxies work. Instead, it reveals the edges of our knowledge. It might be that Hoag's object formed under a very rare set of conditions so unusual that they are not included in the standard model files, or perhaps there is a hidden process at work, something about the way dark matter interacts with normal matter that we have not yet discovered. Most of the time, when astronomers talk about Hoag's object, they mention it in the same sentence as other ring galaxies. But when you place it side by side with these so-called relatives, the differences begin to shine through, almost like comparing a flawless diamond with rougher stones. To truly see how unusual it is, you have to study other famous examples such as the Cartwheel Galaxy, AM0644-741, and the Lindsay-Shapley ring. All of these galaxies wear their rings proudly, but the ways in which those rings came to be are far more common and far less mysterious than the story of Hoag's object. The Cartwheel Galaxy is perhaps the second most famous ring galaxy after Hoag's object. It sits about 500 million light-years away from Earth, and at first glance, it can almost fool you into thinking it is the twin of Hoag's object. Like Hoag's, it shows off a bright outer ring surrounding a dimmer, softer core. But this similarity is nothing more than skin deep. The Cartwheel's ring was forged in cosmic violence, born from a titanic collision. A smaller galaxy once slammed straight through the flat disk of a larger one, creating shock waves that rippled outward. These waves compressed huge clouds of gas, forcing them to collapse and ignite into dazzling bursts of new stars. The result was not a perfect circle, but rather a ring scarred by uneven thickness, jagged edges, long spokes of shining matter stretching outward, and trails of debris cast far from the galaxy's heart. Hoag's object, in contrast, shows none of this chaos. Its ring is smooth, symmetrical, and free of the jagged scars of a violent crash. The galaxy known as AM0644-741, which many call the Lindsay-Shapley ring, tells a similar story of collision. Its ring is thick, lopsided, and filled with clumpy regions where massive amounts of star formation are underway. The ring even shows clear asymmetries, wounds left behind by the uneven path of the shockwave as it tore through the galaxy's disk. Once again, Hoag's object refuses to follow the pattern. Its ring is not irregular or messy. It glows evenly, forms a near-perfect circle, and betrays no evidence of past trauma. This difference is important, because even the most carefully built computer models of galactic collisions always produce distortions. Yet Hoag's ring looks as though it has been drawn with a compass on the blackboard of the universe. There are also the polar ring galaxies, such as NGC 4650A, which offer another kind of comparison. In these strange systems, a ring of stars and gas orbits at a sharp angle to the main disk of the galaxy, almost like a tilted halo. Such polar rings usually form when a galaxy steals matter from a passing neighbour. These structures can survive for billions of years, but they almost always show telltale signs of their stolen origins, bridges of gas linking them to another galaxy, or warping where the foreign material rubs against the host. Hoag's object has none of this. Its ring lies in the exact same plane as the spin of its golden central core, as if the two parts were born together in harmony. Another curious difference shows up when astronomers study metallicity, the term they use to measure how much of a galaxy is made of elements heavier than hydrogen and helium. In galaxies where rings form through violent impacts, the stars on the outer edge often contain more of these heavier elements. This happens because collisions compress gas into starbursts, which enrich the material with new metals. In galaxies with resonance rings, where gravity pulls gas into neat loops, the metallicity tends to match the inner disk, since the gas comes from the galaxy's own reserves. Hoag's object, however, does not fit into either pattern. Its chemical fingerprint is unique, unlike that of its cousins, as though it followed its own mysterious recipe in the cosmic kitchen. Even the way Hoag's ring moves sets it apart. In the Cartwheel Galaxy, and in AM0644-741, the rings are expanding, still growing wider as the shockwaves from their collisions continue to push outward. But when astronomers turn their instruments toward Hoag's object, they find something else entirely. Its ring is not expanding at all. Instead, the stars within it seem to travel in a calm, long-lasting orbit around the core, as though locked into a carefully balanced dance. To some, this makes Hoag's object feel less like the aftermath of a cosmic accident and more like a structure delicately engineered by some unseen hand. Isolation adds to its mystery. Most ring galaxies are discovered in crowded neighbourhoods of the universe, where galaxies frequently bump into or tug on one another, creating the perfect conditions for collisions and gas capture. Hoag's object, on the other hand, sits in lonely solitude, far from any large neighbours that might have disturbed it. This emptiness makes the usual explanations even harder to accept. Because of all these puzzles, scientists struggle to place Hoag's object into a neat category. It is clearly not an impact ring, because there are no scars of a collision. It is not a resonance ring, since there is no internal driver shaping the gas. It is not a polar ring, because its ring is perfectly aligned with its spinning core. With no clear box to place it in, astronomers reluctantly file it under the broad and unsatisfying label of peculiar galaxy, a category reserved for the cosmic misfits that refuse to follow the rules. But Hoag's object is more than peculiar. Its strangeness does not come simply from having a ring, since many galaxies share that trait. Its uniqueness comes from having the wrong kind of ring. A ring that is too perfect, too smooth, too symmetric, too chemically unusual, and too dynamically stable to match any of the familiar stories of galactic formation. From its flawless symmetry to its singular chemical profile, every detail of Hoag's object whispers of a secret origin, one that astronomers have yet to fully uncover. When faced with something as unusual and puzzling as Hoag's object, astronomers often begin with the simplest explanation they can think of. Perhaps, they suggest, it is not a single mysterious galaxy at all. Maybe what we're seeing is just a trick of perspective. Two normal galaxies that, from where we stand on Earth, happen to line up in a way that makes them look like one bizarre object. This chance alignment idea claims that the golden glowing centre we see is actually one galaxy, while the surrounding ring belongs to a second galaxy lying much farther away. From our viewpoint, this background galaxy would look like it perfectly wraps around the first one, almost like a cosmic illusion. At first glance, the theory seems neat and tidy. It would mean there is no need to invent a complicated story of exotic galaxy formation. There would be no mystery about why a vast empty gap exists between the core and the ring. And we would not need to worry about why the two regions look so different in colour and in age. But the moment astronomers tried to put this idea to the test, it quickly began to crumble under its own weight. The first and most obvious problem is alignment itself. For the golden core and the bright outer ring to appear so perfectly centred on each other, the galaxies would have to be positioned with an astonishing level of precision along our line of sight. Even a tiny shift, just a small nudge, would make the ring look uneven, tilted, or distorted. The chances of two galaxies lining up this perfectly, especially in such a lonely and sparsely populated region of space where Hoag's object lives, are unimaginably small. The second problem comes from something called redshift. Redshift happens because the universe is expanding, and as galaxies move away from us, the light they give off stretches into longer, redder wavelengths. Astronomers use redshift to measure how far away a galaxy is. If the golden core and the outer ring were really two separate galaxies, they should have different redshifts, meaning they would sit at different distances from Earth. But when astronomers studied the light from both the centre and the ring, they discovered the redshifts were almost exactly the same. That means the two are not just lined up along our view by accident. They are physically sitting at the same distance from us, and therefore belong to the same gravitational system. The third strike against the alignment theory is the movement of the stars themselves. Careful measurements show that the stars and gas in the ring are moving as though they are tied to the gravity of the central core. If the ring were truly a separate background galaxy, its stars would have no reason at all to care about the gravity of the golden centre, and they certainly would not move in a way that mirrors its rotation. The fact that they do shows that the two structures are locked together, moving as one galaxy. Then there is the strange empty gap between the core and the ring. If the ring were just another galaxy sitting behind the first one, we would expect to see little signs of that galaxy sticking through the gap. Maybe faint spiral arms, wisps of dust, or scattered star clusters crossing in front of the central glow. But the gap is completely dark, as though it really is an empty region of space carved out within a single system. Some defenders of the alignment idea tried one last rescue. They suggested that the ring is not a background galaxy at all, but an illusion created by gravitational lensing. This is when the mass of a foreground object bends and magnifies the light of a background galaxy into a ring, something known as an Einstein ring. But this explanation also falls apart. Hoag's object does not have nearly enough mass to bend light into such a large and perfect circle, and even more damaging, the ring we see does not share the same visual features that real gravitational lensing events display. Even if we were to set all the physics aside, the sheer unlikeliness of the idea is enough to sink it. Astronomers have studied and catalogued millions of galaxies across the sky. Overlaps and partial blockings do happen now and then, but perfect, concentric alignments like what we see in Hoag's object are practically non-existent. For such an alignment to also share the same redshift, the same movement patterns, and the same lonely patch of space is stretching the word coincidence far beyond breaking. By the early years of the 21st century, most professional astronomers had abandoned the chance alignment explanation. Yet, even today, when people first hear about Hoag's object, the idea sometimes pops up again, because it feels like a fun optical trick that could explain the mystery. But the closer you look, the clearer it becomes. The golden core and the shining ring are not strangers who just happen to overlap. They are bound together, moving under the same pull of gravity, caught in a cosmic dance that has lasted for billions of years. Hoag's object is not a case of galactic luck. It is a genuine oddity of the universe, strange, rare, and real. When astronomers study galaxies, they don't just look at their shapes, colours, or how they appear through a telescope. A galaxy's appearance can tell part of its story, but it never reveals the whole truth. To dig deeper into what a galaxy is really made of, scientists need to study its light in much more detail. Every galaxy, every cluster of stars, every glowing cloud of gas has its own fingerprint. And the way astronomers read this fingerprint is through something called spectroscopy. This is the method of splitting light into its separate bands, much like a prism splits sunlight into a rainbow. When this is done, a simple patch of light suddenly becomes a treasure chest of information. From those rainbow-like bands, scientists can measure what kinds of chemical elements are present, how hot or cold the stars are, whether they are moving toward us or away from us, and even how long they have existed. When researchers turned this powerful tool toward Hoag's object, the mysterious ring-shaped galaxy floating more than 600 million light-years away, they were in for a shock. Normally, when astronomers look at a galaxy, they find that different regions tell roughly the same story. The light coming from the central bulge of a spiral, for example, often matches smoothly with the light from the arms. Even in more irregular galaxies, the differences are not so jarring. But in Hoag's object, the fingerprint of the light from the golden central core and the light from the shining outer ring were almost like two completely separate identities. It was as though two very different galaxies had been stitched together into one strange, harmonious but puzzling whole. The spectrum of the core revealed a quiet, ancient population of stars. These stars were older and cooler, shining with a steady golden glow that spoke of many billions of years of patient aging. The chemical signatures in the light were dominated by strong absorption lines, from elements such as magnesium and calcium, exactly the kind of patterns one expects from an old stellar population that has long since stopped making new stars. Just as importantly, the core showed very few emission lines. Emission lines are bright spikes in a spectrum that signal the presence of hot, glowing clouds of gas, often surrounding young stars in the process of being born. Their absence meant that in the heart of Hoag's object, star formation had ended long ago. The core looked like a peaceful elliptical-like galaxy that had settled into quiet retirement after a vigorous youth. But the ring was a completely different story. The light from the ring blazed with a bluish hue, the telltale sign of young, massive and very hot stars. Its spectrum showed strong emission lines from hydrogen and oxygen, which are unmistakable indicators that new stars are being born there right now. The hydrogen lines revealed that the ring was full of gas clouds actively collapsing under gravity, while the oxygen lines told of enrichment by previous generations of stars that had lived, died and seeded the surrounding space with heavier elements. Yet the level of enrichment was peculiar. It was higher than what one might see in some galaxies of comparable size, but oddly lower than what would be expected if the gas in the ring had simply cycled through the core for billions of years. It seemed almost as if the ring's material came from somewhere else entirely. Neither pristine gas from the emptiness of intergalactic space, nor recycled gas from the old central region. Even stranger, spectroscopy revealed that the ring and the core were not moving in harmony with each other. By examining how the spectral lines shifted due to the Doppler effect, the same principle that makes a police siren sound higher pitched as it approaches and lower pitched as it moves away, astronomers could measure how fast the stars were spinning. The results were baffling. The stars in the ring were spinning much faster than those in the core, and the two regions did not seem to be linked dynamically in the way that most galaxies are. Usually, the inner and outer parts of a galaxy are tied together by a smooth gradient in velocity, but here there was a sharp break, as though the two components had formed in entirely different ways. It was almost as if the ring and the core were strangers forced to share the same space. Spectroscopy also revealed a peculiar story about the ages of the stars. The majority of the stars in the ring were younger than the stars in the core, but not by an enormous margin. The difference was on the order of a few billion years, a small gap when one considers the vast timescales of cosmic history. More intriguingly, the ring seemed to have experienced at least two bursts of star formation. One had happened in the relatively recent past, perhaps within the last billion years, while the other had taken place much earlier. The question that gnawed at scientists was why the ring, which seemed stable and long-lasting, would suddenly ignite with star formation long after the core had gone quiet. What event or process could have restarted the cycle of stellar birth so dramatically? The chemical behavior of the gas in the ring deepened the mystery even further. Normally, when astronomers measure the metallicity, the fraction of elements heavier than hydrogen and helium, they can make educated guesses about where the gas came from. Gas originating in a galaxy's own reservoir follows one pattern, while gas flowing in from intergalactic space follows another. But in Hoag's object, the metallicity gradient defied these patterns. The gas in the ring did not resemble the gas of the core, nor did it resemble pristine intergalactic material. It was too enriched to have come straight from the cosmic wilderness, yet not enriched enough to have been processed over and over inside the galaxy. This chemical mismatch was like finding fingerprints at a crime scene that belonged to no one in the known records. Adding to the strangeness was the absence of certain spectral traits. Many galaxies show signs of shock-heated gas, evidence that they have collided with neighbours or experienced gravitational disturbances. But in Hoag's object, these signs were weak or missing altogether. This lined up with other evidence that the galaxy had not undergone a violent event in the recent past, yet it also removed one of the most popular explanations for how ring galaxies form. If Hoag's object had not been smashed into shape by a collision, then how on Earth, or rather, how in the universe, had it come to look this way? At this point, astronomers were convinced of one thing. Hoag's object was not just an oddity to admire for its beauty. It was also a profound scientific riddle, both chemically and dynamically. Its serene ancient core and its lively youthful ring told two different stories at once, stories that did not seem to fit together. It was like listening to two instruments playing in different keys and yet somehow producing a strange kind of harmony. But visible light and spectroscopy could only take the investigation so far. There are many things in the universe that ordinary optical telescopes cannot see. Dust, for instance, often hides the view of galaxies, cloaking newborn stars in thick veils. Cooler stars, which shine less brightly, can easily be missed. Entire structures may remain invisible if they radiate in wavelengths outside the narrow band of human vision. To truly understand a galaxy, astronomers must turn to other parts of the electromagnetic spectrum. That is where infrared observations come in. Infrared light, with its longer wavelengths, can pass through dust clouds that block visible light. It can reveal cooler stars that optical telescopes overlook. It can expose hidden regions where star formation is still going on. When astronomers pointed infrared detectors at Hoag's object, the puzzle only deepened. The first surprise was the almost complete absence of dust emission from the core. Most galaxies, even those with very old centres, retain at least a little dust, leftovers from past episodes of star formation or drifting in from the outer regions. Infrared instruments are especially sensitive to the glow of warm dust, and so it seemed certain that Hoag's object's core would reveal some, but it did not. The central region was almost entirely dust-free, reinforcing the impression that it was pristine and untouched. If dust had been present at any point in the recent past, the infrared detectors would have lit up unmistakably. Their silence spoke volumes. The ring, however, glowed brightly in the infrared. It showed strong signals from both dust and cooler, redder stars. This meant that the ring was not just a nursery for young, hot blue stars, but also home to an older population of stars that had cooled over billions of years. The presence of these older stars suggested that the ring had been in place for a long time, certainly longer than a single starburst. It contradicted the idea that the ring was a recent, short-lived structure, and pointed instead to a long, complex history. Even more fascinating were the details of how star formation was distributed across the ring. To the naked eye, or even through optical telescopes, the ring looked smooth and uniform, without obvious lumps or clusters. But infrared images told a different story. They revealed tiny variations in brightness, little hotspots where newborn stars had heated the surrounding dust. This patchwork pattern suggested that star formation in the ring had not been a simple, uniform process, but rather a series of localized events. The infrared data also allowed astronomers to study the metallicity of the hidden star populations. Older, cooler stars leave different imprints in the infrared than younger ones, and by analyzing these patterns, scientists discovered that parts of the ring had different chemical compositions. This implied multiple inflows of gas over time, each perhaps arriving from a different source. It offered a tantalizing explanation for the ring's puzzling chemical diversity without needing to invoke a major collision. One of the strangest discoveries came from peering into the space between the core and the ring, the dark gap that gives Hoag's object its distinctive appearance. If the gap were merely an illusion created by dust, infrared detectors would have seen through it and revealed hidden stars. But the gap remained almost completely empty, confirming that it truly was devoid of stars. This was important because many other ring galaxies show faint bridges of stars in such gaps, remnants of tidal interactions or collisions. Not so in Hoag's object. Its emptiness was real and absolute. Infrared studies also helped clarify the ring's dynamics. By tracking the movements of cooler stars and dust clouds, astronomers determined that the ring was in a stable, long-term orbit. It was not expanding outward like the rings formed by galactic collisions. This stability, combined with the presence of older stars, suggested that Hoag's object had maintained its peculiar configuration for billions of years. And then there was the halo. Optical telescopes had hinted at it, but only faintly. Infrared images revealed a dim, extended halo of scattered light beyond the ring. This could be the fading trace of an older, larger ring of stars, or perhaps the visible outline of a dark matter distribution stretching far beyond the galaxy's luminous parts. Either way, it added yet another layer to the mystery.